I think you need to unmute yourself. We cannot hear you. No.
So can you hear me now?
Yes, now it's good.
Okay. So I was just giving the introduction.
Okay.
So I have invited Dr. C. Kesava Rao to the dais. He has co-chaired our previous sessions, technical sessions yesterday. I would also like to invite Dr. Naveen Kumar Dhal from CSIR-IMMT to co-chair our session. So just giving a brief introduction to all the participants here, Dr. Naveen has earned his PhD degree in floristic and ethnobotanical studies from Utkal University. He has a research experience of 26 years as a senior principal scientist in environment and sustainability development at CSIR-IMMT. His work has led establishments of herbal gardens and development of state-of-the-art herbarium for sustainable development of biodiversity conservation, creating ample scope for earning revenue. So with this introduction, I would request my colleague Aryan to go ahead with the introduction of our next keynote speaker.
Hello everyone, a very good morning to this session. I would like to take this pleasure to invite Dr. Brajesh Dubey as our first keynote speaker of the day. Dr. Brajesh has done his PhD from University of Florida. He is currently associated with IIT Kharagpur as associate professor in the Department of Civil Engineering. His research focuses on the areas of geo-environmental engineering, integrated solid and hazardous waste management, physical, chemical, and biological processes in natural and engineered systems. He is awarded with Endeavour Fellowship Australia and Ron Crofts Awards Sweden. His current areas of interest include environmental engineering, integrated waste management, life cycle analysis, and sustainable engineering, along with environmental risk assessment. With this, I welcome you, sir, and over to you, sir.
Thank you, Aryan, for the introduction. So you can hear me okay?
Yes, sir, loud and clear.
Good, and you can see the slides as well.
Yes, sir.
Okay, so let's get started. So as I mentioned earlier when I was discussing for this particular talk, so I will focus my talk on circular economy approaches for municipal solid waste management. That's what in the next 20 minutes I'll try to talk about that. So again, thank you for inviting me. So when we talk about this circular economy, when we talk about waste management, when we talk about these environmental issues, I thought let's kind of take a step back and look at why we are even doing all those discussion. What is the big picture out there? Like why we are having this conference, and we tend to have several conferences happening around the world. But what is the basic philosophy, basic concept, why we are even discussing all that? So if you think about, see, our existence on this planet, that's the number one thing that we worry about, isn't it? See, our existence on this planet, when I say our existence, means our generation, future generation, several generations down the line. So we want that Earth should be a safer place for all of us. We should have clean water, clean air, clean soil. We should not get sick because of all these environmental pollution. So all those, that's what we are actually the main big picture goal. Within that, you can talk about sustainable development. You can talk about solid waste management, wastewater, water, air pollution, soil pollution. But ultimately, they lead to the same thing, trying to keep this Earth as clean as possible for us and for our future generation. So to do that, let's look at what has happened to this Earth over its life so far. So if you look at the Earth's age, it's around 4.6 billion years old. Some of the newer research actually suggests that it is even older than that. But let's not worry too much on that part. Let's say it is 4.6 billion itself is a long period of time. So in that 4.6 billion years, if you take the divide that 4.6 billion years in 24-hour scale. Now, why 24 hours? because we are used to 24 hours. There is a 24 hours in a day. So that kind of makes more sense for us. We can relate to it better. So if you put that in 24 hours, 1 second becomes 52,000 years. So that time scale we are looking at. 1 second is equivalent to 52,000 years. 1 minute is 3.1 million, and then 1 hour is 187.5 million years. So in that particular time scale, if you look at it, you start at after like at 0000, which is right after here, and you go all the way here, you see that a lot of things has happened. We'll had the bombardment. We had kind of having some oxygenation, great oxygenation event after almost 10 hours of bombardment and all. When the Earth came in existence, then we have some plant life appearing. Then we had some fish life appearing. Then we had the dinosaurs coming in at around 22:47 hours. Like after 22.47 hours, we get the dinosaurs. The dinosaurs become extinct at 23:40. So they are there for almost for quite some time. So they were the dinosaurs were present. And then if you look at the humans, the present humans, the modern humans, we came into existence at 23:59:56. So this is like just like a railway timetable. So we use that 23 means 11 p.m. in the evening. So 11:59:56, and then after 4 seconds, it will be 24 hours. So modern humans like you and me, we have existed on this planet for just 4 seconds. That's it. If you put that timeline. So 4 seconds means 200,000 years. So humans as we know today has existed on this planet for only 200,000 years. And in 200,000 years, over last few decades more, but over 200,000 years, we have used up a lot of resources. And when we are consuming a lot of material from the Mother Earth, and we are producing a huge amount of waste, and that waste is becoming a nuisance. It has become a problem. You go out, you see that wastewater, you see the problem of solid waste. So it cannot be business as usual. We have to do something about it. So another concept which some of you may have heard about, this actually shows up in the newspaper these days as well, is the concept of Earth Overshoot Day, which talks about like when we are using up all the resources for that particular year. So here the green bar means we are actually consuming those resources. Red bar means we are actually borrowing resources from our future savings. So what does that mean? Say 1970, we used whatever the Mother Earth can produce in that particular year, we were using it up to almost the end of December. So whatever we were getting it from Mother Earth, we were using it. So whatever is the renewable resources available to us, we were using that for that particular year. Now, over the years, that has kept on moving from December to November to October to September. Now we are even in August and July. Last year in 2019, we were actually, it was 29th of July. In 2020, because of pandemic, because of the COVID pandemic, everything was shut down. It went up to August 22nd. So what does that mean? That whatever resources the Mother Earth could provide us in 2020, we used all of them by August 22nd. For rest of 10 days of August, September, October, November, December, we borrowed resources from our future, like reserves. We cannot, like if you can compare that, see with your salary. For example, say that somebody is making 12 lakhs a year. Now, if you use the 12 lakhs, entire 12 lakhs by August, so September, October, November, December, what will happen? You will either take money from your savings, you will try to borrow from someone. So if we do that, after a few years, we will be bankrupt. So that is what we are doing to Mother Earth. We are making Mother Earth bankrupt of those resources by consuming a lot and producing a lot of waste. And that cannot happen forever. So that's where the circular economy comes in picture to change that. The circular economy says that we need to have a systemic approach to economic development and design it to benefit business, society, and environment. We cannot have the take, make, waste linear model. Right now, what it is there, we go to mining, take the material, make product, use the product, dump it into the environment. That cannot run forever because we are running out of resources, as you saw in the previous slide as well. So what we need to do, we have to stop producing the waste. Waste is actually a misplaced resource. So we have to bring that waste back. So rather than wasting it, we have to reuse, repair, recycling sector, bring that waste back into the economy, do lots and lots of resource recovery, and then gradually decouple growth from the consumption of finite resources. So this is a very strong concept, and it is being taken up in many countries around the world, including in India to some extent. And this is where the future is. We cannot have business as usual of linear economy because we are running out of material. We have to focus on resource recovery of the waste, and then try to move towards zero waste. So that's what the whole goal is all about. And then we did, well, how that will happen? We have to design things better. So as a waste management engineer or the environmental engineer, rather than having the end of life approach, where end of pipe approach, where you worry about when it only becomes a problem in the environment, you get involved from the very beginning, like how to design the product so that we can do this resource recovery better, how to design products so that recycling can be done better, how to design products so that we can try to keep the high toxic material away from the design of any product. So those are the thinking that is already started coming in, and that's where in next 2-3 decades, that's where the economy has to move, because we don't have any other option. And we have to design our system in such a way so that will be design out waste and pollution. What if waste and pollution were never created in the first place? So that's is the circular economy concept, is that let's design out the negative impact of economic activity that is damaging to human health and natural system. Look at what is happening. Say, for example, we had COVID, and then schools and colleges were closed. Now because of pollution, our brothers and sisters in Delhi area cannot go to Delhi NCR area. They are not able to go to colleges. They are not able to go to school. Is that what the future we want? Of course not. So that's where these things comes in picture. Let's try to design in such a way so the waste and pollution is not there, reduce the greenhouse gas, hazardous substances, and so on and so forth. It kind of gives you an example where you can have a circular economy. Your wastewater treatment plant can go, the sludge from there can go to this energy factory, clean water can go for usage. For this, from the households, the wastewater go to this plant, then organic waste can come to this energy factory, organic waste from households can come to an organic factory, as well as from the industry. Then the manure from the organic, from the farming, it can come there, and all together can produce biogas, can produce electricity, can produce heat. We can do phosphorus and nutrient recovery. We can make organic fertilizers, which could be used for agricultural purposes. So as you can see, that one waste from one sector becomes a resource for the other sector. So that's kind of concept has to come, and that's what some places already happening, like Helsinki metropolitan area, they're working on that. Singapore is doing a big way in terms of that as well. So we have to build an economy that uses things rather than uses them up. So we have to design our system in such a way so that we can keep on using it again and again and again. So that's what the whole concept. So in Indian context, why it is important? Say we might be thinking that yes, these are all the Western world, Western European countries are working on it. Why we should worry about that sitting in India? Because if you look at this particular projection, which came from it's called Framework for Indian Resource Panel. In 2015, they come up with that. So this side is the projected number. These are the actual numbers. So you can see by 2050, we will require a lot of biomass. We'll require non-metal minerals. We require lots of fossil fuels. We require a lot of metals. And all these cannot just come from virgin material. Right now, 94% of our manufacturing is happening based on virgin material. Only 6% is based on recycling material. That 6% has to go up, because these virgin materials are becoming costlier and costlier. Mining is becoming difficult. Mining is having a huge environmental footprint. So we need to kind of move towards this secondary mining. It's called secondary material. So the future needs for India for resources and a dimension and challenges in terms of resource availability, affordability, and sustainability. It makes it clear that resource efficient production process and use of secondary materials are inevitable to meet both growing demands and supply constraints. That's what this panel report said. And that's where this waste management comes in picture, where whatever waste is produced, we cannot just dump it into the dump site. We have to do a lot of resource recovery. Now, how we will do that? So this was the World Bank report, which says that 2 billion tons of municipal solid waste in 2018, and the number is going to go up to around 3.4 billion tons by 2050. What is there? Metal, glass, plastic, cardboard, and some green waste. Individually, all of these could be we can do resource recovery from them. These can be recycled. These we can do biocomposting, like composting or biomethanation plant. Why it is not happening in a country like India or many other countries? It's again, if you look at what is the scenario, in many countries, European Union, which does the best job, is still around 30%. The top here is the waste production. Second one is recycling. Third is the waste to energy, resource recovery. Fourth one is the landfilling. So as you can see, nearly 30% of the waste is still goes to landfill in European Union, which does actually the best job in the world. And many countries, if you look at the India, 91% landfilling, China, 79%, Brazil, Africa, 100%, Brazil, 100%, Mexico, 100%. So most of the world's waste is just ending up in the landfill, where it should not end up. So if you are a good solid waste engineer, you have jobs available around the world, basically. That's what I'm trying to tell you. So there is a huge job opportunity there. So then why it is happening? The major problem is the lack of source segregation. If you don't have proper source segregation, then you cannot do anything with that waste. If all the waste gets mixed up, it's very, very difficult to do to do anything with that waste. We have to do the source segregation, at least wet and dry, as our municipal solid waste rules also says that you have to do source segregation. And not only doing source segregation at home, we have to collect the waste in a source segregated way, take the waste all the way to the treatment center as in a source segregated way. Then only it's going to work. Otherwise, it's not going to work. So that's the number one message if you want to take out from this talk, that for effective waste disposal, segregation is the key. You can go to Economic Times, and this was I wrote almost 4 years ago now. And you can read about that in detail. There was much. I've just put a screenshot here. It was a much longer article, and then you can read about that. Why I'm telling that the segregation is key. India, we produce quite a good amount of waste. Only 70% is collected, and out of that, only 30% is getting treated. Rest is getting into the landfill. We have worked on several rules and regulations over time. A lot of rules have come, but the problem again comes is the lack of proper infrastructure on the ground. Having a lack of proper infrastructure. Our ULBs needs a lot of capacity building, where they need to have good trucks. They need to good physical capacity. They also need to have intellectual capacity. We need to have more and more training programs in the waste management sector to get the people on board, talk to the people, and then try to have an integrated waste management plan. For every city in the country, we need a proper waste management plan. How will do that? You start with what is needed, identify your need, review your existing system, look at the regulation, then come up with what kind of decision you will make. What is the objective for that particular city? See, waste management is not one size fit all. What will work for Bhubaneswar may not work for a smaller city because of the economy of a scale. What will work for Bhubaneswar may not work for Jaipur because there is a different climatic conditions, different kind of market available. Say you make all the compost. If you're not able to sell that compost, what is the point of making that compost? So there is a lot of factors, local factors comes in picture, type of food habits, type of garbage. So these are all very, very important parameters that has to be looked into. So of course, we have to follow the broad guideline of the federal rule, but individually, every city and town has to come up with their own kind of what will work in their area. And based on their limitations, based on their geography, based on their demographics. So you establish the objective, look at what kind of solutions you will come up, compare option, develop plan, implement plan, and then you reevaluate the plan every 4 or 5 years. That's all. Like you make a plan for 25 years, every 4 or 5 years, you have to reevaluate the plan to see what is working, what is not working. With the things which is not working, why it is not working. And then we have to kind of do this, and that exercise will take our waste management infrastructure in a better place. And throughout the process, education, public participation, and outreach is very, very important. Once we kind of understand what is there in the garbage, to do a very good job of understanding of the quantity of the garbage and quality of garbage, there are several technologies are out there which you can actually take. There are a variety of technology based on the type of garbage. You can choose this technology. You can even use a life cycle assessment tool to look at which one has a better environmental footprint, and you can do a proper decision making based on that. But whenever you make decision making, you should reevaluate the decision too. For example, if you look at here, I will take another maybe 2-3 minutes. I think I'm almost I have around 1 or 2 minutes left. So another 2-3 minutes. So in terms of but I'm telling that you have to look at your decision making, whether why the decision is correct or not correct. For example, here, waste to energy is we are working on a lot of waste to energy. We have around 69 megawatt operational plant. This data is slightly older, maybe around 2 years old now. Then under construction is 84 megawatt. Proposed is 383 megawatt. But the most important is here, there is a non-functional of almost close to what is operational. 66 megawatt is non-functional. Now, why they are non-functional? Are we going to see an increase in this bar in coming years? We don't want to see that. That will be a lot of waste of money of the country, a lot of waste of resources of the country. So why it is non-functional? What has gone wrong? And are we using the same technology, similar technology at similar place otherwhere? Are we going to see another failure? So that kind of critical analysis is required. Because see, what happens is many times we get so much emotionally, as Indians, we are very emotional people. We get so much emotionally attached to one particular technology or one particular idea that it's very difficult for us to backtrack from there. If it's not working, let's backtrack. Let's look at why it is not working. Can we make it work? And if we find out that it's not going to work in India, let's stop doing it. Let's move on something which will really work in India. So have to have a holistic approach. Have to, and don't come up with a solution which just kind of band-aid kind of solution, not really total solution. I'll give you an example here, although it's not from the waste management. Say this gentleman is driving a diesel vehicle and he's having all those emissions. He feels, oh, he's polluting so much the environment. He moves and buys an electric car. Now, electric car is all the energy required for the electric car, for the charging his batteries and other stuff is coming from coal-based thermal power plant. Like right now in India, we have more than 50% of the energy is coming from there. So if you today, if you move all our vehicle to electric car, are we really solving the environmental problem? Actually, the answer is no, unfortunately. What we are doing is, yes, we will reduce the air pollution in the cities to some extent. Vehicular air pollution will go down, but if we don't invest in renewable energy, in solar, thermal, and all those, which we are doing right now, but what the study showed, like we did a study and we saw that we need at least 70% renewable energy source to make really this electric car beneficial for the environment. So we have to work on that aspect. Just using electric car while using coal-based thermal power plant is actually not going to help the environment that much. So you need to have a holistic approach. If you only look at this, you don't look at this picture, then everything looks so rosy, isn't it? Electric vehicle also requires batteries. The battery requires a lot of critical metals. The critical metals are very difficult to do refining and do mining. And most of those critical metals are coming from China. So we have to depend on the import from China. So there are a lot of things are there. It's not that easy. But unfortunately, what happens is when we decide, once some fashion comes, like this is good, then of course everybody we start following blindly to that. We have to do a lot of critical thinking in all these things as well. So very quickly, I'll just show you some pictures from Vizag, which we have worked in great detail with the Visakhapatnam Municipal Corporation in terms of looking at their waste management. We did a detailed study over there. I'll just show you some pictures of quite a very good work going on in Vizag, where they are collecting this food waste separate. And they are of course, there is a lot of room for improvements in terms of the quality of dustbins and all that. Quality of this infrastructure needs a lot of improvement, but they are making a lot of effort in terms of doing a wonderful job in terms of waste collection. And then they are having this compost plant where they're making this compost. We're able to sell those compost. Vizag is not too far from agricultural area, so they can able to sell. There is also looking at the waste to energy project very critically in terms of how to recover the landfill which they have. And of course, some of the newer machines are also showing up. So in terms of if there are some students in the audience, for their benefit, just to let you know, we are working on a lot of projects these days on looking at our resource recovery from a circular economy approach, resource recovery from kitchen food waste, organic waste, of municipal solid waste, trying to come up with a lot of value-added products. So if you're interested to work with us as a PhD students or something, you can always contact. And if you're more interested to learn about environmental engineering, about waste management and all that, you are more than welcome to join some of these SWAYAM NPTEL courses, which is available through the MHR Ministry of Education NPTEL platform. So this course will be running in January. It's a basic course on environmental engineering and science, fundamentals and sustainability concept. There will be a course on e-waste management as well in January, February timeline. And then this course will come later in the year. This was offered last time in July. So there is a course on integrated waste management for a smart city, where we talk about what I tried to tell you in the last 20 minutes. We go in great detail on that in 12 weeks. And then there is also the whole concept of sustainable engineering, life cycle, and circular economy. There is another course on that, which is around 8 weeks duration too. So these are all my students who really work hard and then we are able to do quite a good amount of work in this particular area. So work with some of those international collaborations as well. So thank you for the attention. If there is any question, I'll be happy to take that.
Thank you so much, sir, for this insight. I would request Ria to kindly look after the questions that are there.
Thank you so much, Arif. If you have any questions,
In the meantime, I would request the participants, like if they have any questions, those who have joined online, they can just raise their hands and then we can take these questions.
he'll not be able to hear you, sir. Yes, sir. It is not clear. Yes, sir.
Hello. Yeah. Good morning, everybody. Dr. Dove, am I audible?
Yes, you are. Yes, you are.
Yeah. Dr. Dove, I'm.
Oh, you got muted now. I cannot hear you now.
Please unmute the podium mic. Yes.
Yeah.
Hello.
Yes.
So, Dr. Dove, I am Dr. M.K. Dhana, Chief Scientist and Head Environmental Research. What is the problem?
Now the podium is muted. Cannot hear. Yeah, I cannot hear.
So
No,
kindly unmute the podium mic.
Yeah, there seems to be some background, maybe or when they are trying to talk on the podium mic, there is a echo.
Yes,
so,
sir.
Yeah, no. Yeah.
Hello.
Yes. No.
लूप बनेगा हेलो
Yeah.
बंद करो वो तो लूप बनेगा ना स्पीकर ऑफ करो
Yeah, probably that's what.
Is it okay now? No? No. बाहर का आउटपुट ऑफ करो ना
So we can switch off the podium mics and you can speak directly to the mic, the laptop. I think that will do.
No. The sound has to be ingested in Zoom. Yes. Sound is ingested in Zoom. ठीक है. या तो total sound off करो. Total sound off करो. Total off कर दिया. Hello.
Yeah.
Can you hear now?
Yes. Yeah, loud
I'll
and clear.
switch on the mic speaker here.
Yeah, it's clear.
Yeah. Now you can hear.
Yes, loud and clear.
Yeah. So we are using the laptop. The audience can't hear now. So they will probably hear the pre-recorded one. So you can ask questions. Yeah. Okay. And it was a brilliant presentation, by the way.
Thank you. Thank you. Thank you.
Yeah. Professor Dubey.
Yes.
The excellent presentation. I am Dr. N.K. Dhar, Chief Scientist and Head Environment Department of CSIR located in Bhubaneswar.
Okay.
The excellent presentation. We'll be in touch with you. One thing just I
Sure.
want to know from you, Dubey, any smart city development work you are doing in Bhubaneswar?
No, I am not associated. We did the Indo-German workshop. I don't know. Indo-German workshop was done in Bhubaneswar. I was there as part of that workshop. That was, I think, almost now more than 3 years back. But after that, no, I'm not involved. Unfortunately, I would like to work in Bhubaneswar. I'm doing some work with Vizag, and I worked with Guwahati. Guwahati, we have done some work. We have done some work with Kolkata and like a new town because that's the smart city there. And Kolkata Dhapa side also we did some work with the existing landfill. There were some issues. We did some work, and little bit work I've done in Ahmedabad too. But these are the places unfortunately. Somehow I could not connect with someone in Bhubaneswar to work there. I love Bhubaneswar city. I like to go there, but so it will be really
okay. The way we'll be in touch with you. Any work you are working related to wastewater?
Yes, right now we are working on wastewater. Even that I'm trying that Mohapatra. I'm trying to remember his name.
A superintendent engineer.
Yeah. So
water resource department.
He is our alumni. He is an MTech from IIT Kharagpur only.
Okay.
So yeah, I met him a couple of times. Yeah, in wastewater we are right now we are trying to. If you come to IIT Kharagpur, I'll show you. We have a plant where we are taking the campus wastewater and make it almost as clean as drinking water. I'm saying as clean as drinking water. I'm not saying drinking water because of we haven't tested for pharmaceuticals and those medicinal compound. So I'm not calling it a drinking water, but it's almost very clean. We are using it for horticultural purposes. So almost we can use it for any purpose other than drinking water. So we have a plant going on, demonstrating plant going on. So yeah, just if you, I think if I can, you can get my if you say somehow.
Okay, I will contact you later on because in our department, one Dr. Ashish Kumar Yadav, he is working on constructive wetland development, and we have transferred the technology. Now he's in Spain. Anyway, there is good lecture. So I will be in touch with you. Take care, Dubey. I will take your address and we'll see that some work can be done for smart city for Bhubaneswar. Okay. Thank you.
Okay.
Thank you.
Thank you. Okay. Thank you. Thank you.
I would like to know if there are any further questions from the participants who have joined online or anyone who is there in the offline.
Offline, there are no questions, Aryan.
Okay. So with this, I will thank you, sir, for your wonderful presentation. I hope this has drawn certain insights in the mind of the participants and they'll think into this perspective. Thank you so much, sir, for your presentation.
Thank you. Thank you.
Moving on to the next keynote speaker, I would like to invite Dr. Popita Das. Dr. Das is associated with the Department of Chemical Engineering, Jadavpur University, Kolkata as a professor. Her topics of research include wastewater treatment, bioremediation, biodegradation, bioabsorption, biofuels, membrane filtration, biopolymer, etc. She has won several national and international awards of repute for her contribution to science that include the National Award for Technology Innovation for the nomination of novel biodegradable natural filler reinforced hybrid polymer composites under the category of green biodegradable polymer by Department of Chemicals and Petrochemicals, Government of India. She is also ranked in the world ranking of top 2% scientists in 2021, published by Stanford University in the field of chemical engineering. With this, I welcome you, ma'am, to the session. Dr. Das, can you hear me?
Okay. Should I share screen or yeah?
Dr. Das, I'll share
I
the
hear you.
presentation from my end.
Can you hear me?
Ma'am, your voice is a bit low.
Hello.
Yeah, it's audible now, ma'am.
Can you hear me?
Yes, ma'am, I can hear you. I'll share your presentation from my end, ma'am, and you just say next when you want to
Okay,
change the
I
slide.
can do it also. Okay. 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 Do it. Good morning, everyone. My topic is on role of carbonaceous materials on wastewater treatment. In
Dr. Das, we are losing you. We cannot hear you.
Dr. Das?
Dear participants, we are just connecting Dr. Das over phone so that we don't have any network issue.
This next.
Yeah, ma'am, we can hear you. You can start presenting.
Okay. So my presentation is on role of carbonaceous materials
In
on wastewater treatment.
Treatment.
So,
materials
in that different
have
carbon-based materials have
properties
unique properties
such as high
Ma'am,
such as
ma'am, just to interrupt you, ma'am,
That's
can you
what
just
basic-
mute your Zoom? Yeah, now it's better, ma'am.
Aye. So these materials can combine with other elements or materials to form strong covalent bonds. So due to unique properties, versatile nature, they have been widely used in different ways. Researchers have been used different types of carbon-based materials to remove the pollutants. Next. So you will see that there are different types of pollutants is coming from, in water bodies and it pollute the water body. So these pollutants are maybe dye, maybe PCP, that is a different type of organic cardboard, organic materials coming from pharmaceuticals and persistent pollutant materials. And such uncontrolled amount of PCP may lead to toxicity, drug dependency, and drug resistance. Next. So these pollutants may pollute the environment, and these industrial effluents contain various toxic metals, harmful gases, and several organic and inorganic compounds. So to remove these materials from the water bodies, carbonaceous materials have a big role because these materials have different unique properties. So there are different agricultural waste like rice, sugarcane, sawdust. These can be used to which have lignocellulose material. These materials can also be used to remove the pollutants from the wastewater. These are all carbonaceous materials. So for that, what we can do, we can use the carbonaceous material that are coming from different agricultural fields, that is the waste material, which can be used to get a different carbonaceous material, and from which we can use it for the removal of the pollutant from the wastewater. First thing is the first carbonaceous material which we can say that it can be used is the activated carbon or activated charcoal. So activated carbon is used more efficient due to its large surface area, high catalyst activity, and its porosity. Agricultural byproducts have been considered such as different shells, rubber wood sawdust, peanut hull, coir teeth, as well as rice, sugarcane, etc. So the unique properties of it is that its better removal efficiency with low mass useless, high surface area, better separation of the treatment, cost effective, easy degradation, thermostability, durability, and chemical resistance. So due to this advantage, activated carbon is used in different industries, and the cost is also very low, very cost effective process. Time requirement to treatment of the procedure is also very low. So we can use it in the treatment of wastewater. Now, second one is the cellulose, which we can get from the moist lignocellulose material, and it is biodegradable, renewable, natural polymer. So from it, we can use cellulose as well as we can use nanocellulose. In case of nanocellulose, which makes it a very efficient material in membrane and filter. So it has another property, that is the organic fouling and biofouling reducing capacity. So cellulose is also used as one of the absorbent materials for the removal of the pollutant. In case of cellulose, the benefit of using cellulose as an absorbent is that it has high modulus of elasticity, low production cost, source is abundant, easy processability, eco-friendly, and high stability is in most organic solvents. So cellulose as well as nanocellulose is used in different literature. One of the literature is that where they have used the cellulose nanocrystals as functional material in chitin and matrix, and it is observed that 70 to 98% removal of dye can be possible within 24 hours. Whereas porous cellulose bioabsorbent is also used in grafting in acrylic acid and acrylamide to remove the anionic dye. So from this study, it is observed, it can be said that the cellulose nanocellulose both can be used as an absorbent to remove the dye material. Then another and improved one is the carbon nanofiber, where these are fibrous materials that are obtained as a result of electrospinning. So it is also efficient due to its controllable texture, tunable, and their special physicochemical characteristics. High porosity, high specific surface area, which is important for absorption process, is observed in this carbon nanofiber, so the absorption capacity is also very high. So advantage is also low cost, burst material selection, and versatility. Then another sophisticated one is the carbon nanotube, which is now used in different purpose also. So one of the purposes we have used in the wastewater treatment. So carbon nanotubes can have one single wall that we call as single wall carbon nanotube, or more multiple sheets of graphene rolled into a hollow cylindrical shape with outer diameter of 1 to 100 nanometer. So why we are using carbon nanotubes? Because it has also unique chemical and physical, mechanical and thermal properties due to the cylindrical structure, nano size and high aspect ratio of length to diameter. So this also is used in biosensors, in optical components, in electronic transistor, and mainly as adsorbent for the removal of toxic pollutants. So in structure, you can see that slide number 13. You can see that there are different type of structures of carbon nanotube we can use. Where one is a single wall, second one is a multi-wall, and third one is the double wall. Now, surface. Not only that, one of the property of CNT is that oxygen functional groups are present like hydroxyl, carbonyl, and carboxyl on their surface. Not only that, we can increase the surface functionality using different chemical and other processes like using different acids, different ozonation or plasma technology, and so that we can functionalize the surface properties of a carbon nanotube so that we can use as a better efficient absorbent for the plant. Now another sophisticated one is which is the atomic layer of sp2 hydrogen carbon densely packed into a two-dimensional honeycomb network. So that is also nano size, very thinnest, its strongest material known being both brittle and simultaneously. So, and this can be wrapped with different materials so that the efficiency will be higher, like zero-dimensional polyethylene rolled into one-dimensional CNT, or can also stack into three-dimensional graphite. So, a hexagonal unit cell of graphene comprises two equivalent sub-lattices of carbon atoms joined together by the bond of 0.142 nanometer length. So, if we see the structure in slide number 17, we can see that this looks like a honeycomb structure. So, unit cell contains two atoms, each one belonging to a different sublattice. So, we can use this graphene as a basic building block, and we can mix it with different materials. Figure 4, slide number 18, where we can see that it can be used with a polyethylene rolled into a carbon nanotube or three-dimensional graphite. We can use a graphite also to get a building block of graphene with the different materials. Now, these are the properties of graphene, where you can see that the bond length is 0.142 nanometer. EG surface area is also very high, 2630, like that. Then Young's modulus, tensile strength, all are very efficiently, all are very high, so that it can be used efficiently for the different instruments, as well as in our case the surface area is higher, so absorption will be also be very high. Another one is the graphene oxide. So it is a highly oxidative form of graphene consisting of variety of oxygen functionalities in its graphitic backbone structure like carboxyl, then carbonyl, and epoxy, as well as hydroxyl group. So like graphene oxide is oxidized form of graphene. So in that case, in graphene oxide, we will see that the absorption property is higher in most of the cases, not all the cases. We have seen that graphene oxide activity in case of absorption or in case of wastewater treatment is higher because different oxidizable groups are present there, like carboxyl group, carbonyl group, hydroxyl group. So due to and we can functionalize the group also. So it can be characterized as unconventional soft materials such as a two-dimensional polymer, then colloid soft membrane, liquid crystals, etc. So as graphene or graphene oxide is nanomaterials, we can coat it on the other materials, and the efficiency will be higher. So this is the structure, slide number 22, where we can see the structure of a graphene oxide, where we can see that the different groups are present there, carbonyl group, OH group, etc. Not only that, like carbon nanotubes or other components, we can also functionalize the structures of graphene oxide so that more oxidizable groups can be introduced into the system. Not only that, again, this graphene oxide, on that graphene oxide, we can introduce different types of metal oxides also, or graphene oxide we can coat in different biogels also. The advantage is that biogel has some adsorption property, or activated carbon has some adsorption property, and graphene oxide is also there. So this material may have the its adsorption efficiency will be higher in the process. That is, the wastewater treatment efficiency will be higher. So for this advantage, we can make different type of carbon composites, which include carbon nanotubes, glassine, fullerenes, carbon nanofibers, metal oxide, and activated carbon. The pure of coating carbon adsorbent eradicates the problem of poor oxidation resistance. So in all the cases, we have seen that different type of carbonaceous materials may be used for the treatment of wastewater. In case of cellulose, you have seen that we can extract the cellulose from different agricultural waste materials, mainly lignocellulosic materials. So I cover here only the cellulose part, but that we extract the cellulose from lignocellulosic material, and then we are using it for the removal purpose. Not only that, this cellulose from the lignocellulose material, mainly for the biofuel generations or other purpose, we discuss the lignin and the hemicellulose part. But that lignin is also have the capacity to remove some of the pollutants present in the wastewater. So that lignin part is also useful, which we can use further for, of course, we can extract different types of valuable chemicals from the lignin also, from hemicellulose also, but not only that, we can use for the wastewater treatment also. So waste materials is now here used as a valuable material, from where we can get the biofuel we can use for the wastewater treatment of cellulose, using the cellulose, nanocellulose, as well as the lignin, as well as hemicellulose also. So these are the different synthesis processes of graphene oxide. Mainly we are considering the Hammers method, and then we are considering the different modified Hammers method. So in modified Hammers method, different researchers are using different types of oxidizing agents to increase the oxidizable property, increase the OH or RCOH group presence in the graphene oxide structure. So synthesis of carbon nanocomposite, that also can be used using different procedures like chemical vapor, coarse cell, matrix based, ball mill method, salt gel method, solvothermal method, polymeric precursor method. Biogel preparation, we mainly use the sodium hydroxide or zinc chloride treatment, and then we can use at higher temperature. We can use in inert conditions using nitrogen purging or other component, other gaseous component, inert gaseous component purging, and we can get the biochar. So this is one of the process of cellulose extraction from raw adsorbent. So this is the preparation of cellulose fibers using the acid hydrolysis process. We can use the alkali hydrolysis process also, but here we have used the acid hydrolysis process because here we have seen that in acid hydrolysis process the extraction was better in this particular case. So in our lab we have used different type of we have extracted different type of carbonaceous materials like rice powder, rice ash, from rice as well as other components also, cellulose, then silica also we can extract it from the from the rice. Not only that, we have make a composite of graphene and other matter using the TVA chitosan polymer composite, and we have seen that the first one is the before treatment and after is the after absorption. We have seen that we have used here a dye material, and we have seen that this composite material, the color is changing as it absorbs the dye from the material. The advantage of this TVA chitosan polymeric composite is that in that case, as it is biodegradable, so after absorption, one of the problem of absorption technology is that to discuss the whatever the absorbent shall be used in the study. So as it is biodegradable, so after treatment, the removal is that biodegradable polymer composite, we can degrade it using different type of organisms, so removal will be higher. So this is another type of composite we have prepared from PBA chitosan carbon polymer composite. So applications of this carbonaceous material for different wastewater treatment. So you see that.
Ma'am, sorry to interrupt you. Ma'am, due to time constraints, I would request you to kindly wrap the presentation.
Okay, so these are the different composites we can use, pollutants we can use to remove the, these are the different carbonaceous materials we can use to remove the different types of pollutants. So, not only that, pharmaceutical components also we can remove it from the pollutants. So these are the different pollutants we have used to remove using the extracted or synthesized nanoparticles and carbonaceous materials. So these are some of the results I can show you. And these are some of the publications on the same topic. So this is my students. Mostly they are PhD students. Some of them are MTech students also. Thank you very much.
Thank you so much, ma'am, for the presentation. Now, over to you, Ria. I would request the participants who have joined online, if they have any questions, they can just raise their hand and we can take their questions. Ria, kindly unmute the podium mic. Yeah.
I think it is okay.
Thanks, Dr. Bhubaneswar, for giving a very good lecture. Are you audible?
Yes, sir, we can hear you.
No response.
We can hear you.
Yeah. So this is a question for this Dr. Bhavita. So what is the surface area you are calculated from all the absorbents? And that is the main role in this absorbent. So have you calculated the surface area of each absorbent?
Yeah, we have calculated, we have determined it using the BG surface area analyzer. And mostly in graphene oxide, the surface area is higher. Like whatever we have synthesized in our lab from different graphite materials, as well as from the rice also we have used to extract, to synthesize the graphene oxide. So in that case, mainly the surface area is around 500 to 1000.
One more thing, you are used some functional groups for this carbon nanotubes and other things. So what is the main role of functional groups? You are using this carboxyl groups and other groups also. Can you
actually, we have functionalized the materials, mainly graphene oxide and other biochars also, so that if we have the anionic dye or cationic dye, so depending on it, we have functionalized the structure of the graphene oxide or other structure. Till I can hear you. Yeah.
The graphene. Hello.
Sir, can you please repeat the question?
Yeah, the graphene you are given this. Are you purchased or market, or are you synthesis in our laboratory? Graphene.
Dr. Popita, sir is asking that have you synthesized this graphene in your lab or you have purchased it?
Yes, like that.
Okay, thank you, Dr. Babita.
We have synthesized graphene oxide, biochar in our lab.
Okay, so ma'am, there are no further questions. Then thank you so much, ma'am, for the presentation.
Thank you.
Moving ahead with you, Ria.
Okay.
Am I audible?
Yes, you're audible.
So moving along the agenda, we have our next presentation by Dr. Shantanu Mukherjee. Dr. Shantanu is an assistant professor at the MS Swaminathan School of Agriculture, Shulin University. He has received multiple accolades such as the Indian Japan Hiyoshi Young Leaf Award, EGU Young Scientist Travel Award, and many more awards for his work. His research interest includes the fate of emerging contaminants, biogeochemical transformation of nutrients, and the role of dissolved and particulate organic matter in the deciding contaminants' fate in the environment. I would invite Dr. Shantanu over the dais to give his talk on biochar for waste management and environmental remediation, a green and sustainable technology.
Very good morning to all of you. So I think my previous speaker has done a very good job for me. So I think I don't have to work much on it. So just a brief, you all know about what is biochar and why we use biochar. So I just give a brief overview about the agro waste management. As an agricultural scientist, I think I should work on that. So we know that some problem statements. So India generates almost on an average 500 million ton of crop residues per year, as per the Ministry of Renewable Energy. And the generation of crop residues is highest in the state of Uttar Pradesh, followed by Punjab and Maharashtra. And crop residue burning is a big issue. We know every time in this year, we see even also a few weeks back in the Delhi that there was a huge pollution and the air quality index is almost 430, 400. And now there is a lockdown because of the air pollution issue. So it creates a threats to the human and environmental health because it gives almost average annual CO2 production of 40 million ton. Other than this agricultural waste, there are also kitchen waste. And my previous speaker also put some light on that. And it comprises almost 50% of the total solid waste. And a staggering 50 kg of food is thrown away per person every year in the Indian home, as per the Food Quality Index Report 2021. And the food wastage problem has generated or has created the worst situation in the generation of the waste biomass. And improper disposal not only creates a situation where more than 1 billion ton of CO2 emissions per year have happened. And you see a table where you see that India almost generates 500 million tons per year of agricultural waste in comparison to the other countries. I am in the Himalayan region in Solar University. There is a big threat in the Himalayan region, we all know. That's the pine needles. Pine needles acts as a catalyst for the forest fire. And we know in that region, Uttarakhand, Himachal, every year there is in the news, we see that forest fire problem. So northwestern Himalayan region is endowed with the cheer pine. And there are a lot of coniferous trees, pine, deodar, spruce, they looks beautiful, but all glittering are not gold. So Himalayan pine needles are considered as one of the prime biomass or waste material in the northwestern region. And they are found in abundance is more than 7 million hectares. And forest fire, because we know in the pine needles, they have terpenoid compounds and they act as a catalyst for the fire. And it's a natural hazard, we know. Forest fire in the northeastern Himalaya, it's considered as a Indian National Disaster Management Authority, although it's not declared as a natural hazard, but there is a loss of. Other than that, in the Himalayan region, in the Solon region, there is one of the Asia's largest pharmaceutical industries. And they are creating a lot of pollution to the water. And because they are in that region, that water flows to the Punjab Straits, and there's a PPA area, Bardri, Baruti, and Nalagarh. And all giant pharmaceutical companies are situated there, starting from Sun Pharma, GlaxoSmithKline, even some COVID vaccines were produced there in that region. So now the biochar. What is biochar? It's not a new thing. Biochar is a solid carbonaceous material. When we produce it from the agricultural waste, then we call it biochar. If we produced from other than agricultural waste, any woody materials, then we call it charcoal. So this biochar was started from the Amazonian dark earth by pre-Columbian Indians from 500 to 2000, 5,000 years before. So in the Cornell University, US, people have done extensive work on the biochar for agricultural purposes. And it has so many purposes. It can use for carbon sequestration also, and also is a good tool for adsorbent of the contaminants. And soil organic carbon. Nowadays, people are talking of the carbon. To keep organic carbon in the soil is a big thing. It's $1 million question. How we can keep the soil carbon restoration. Yesterday, my talk was Dr. Manish Kumar. He mentioned that biochar can be a good component for organic agriculture. That's absolutely true, because we need to have this more carbon, and we have to keep a good environment so that our soil can become healthy. So not only human health, we have to also keep for the soil health to produce good and sustainable agriculture. So biochar can produce from the different feedstocks, and it can be produced from the cotton husk, rice husk, or any other waste material. And it is produced under pyrolysis congestion in the limited on the very slow presence of oxygen in the different temperature range from 400 to 1000 degrees centigrade. And as I mentioned, it's a good tool for solid waste management. It can be used as adsorbent. We also know that in the COP26 summit that is ended in the Glasgow, our Honorable Prime Minister has told that India should reach the carbon neutral by 2070. So now we are looking for the carbon neutral sources or carbon neutral energy. So we can say that with the biochar, we can have a carbon negative. Carbon, of course, it's not a carbon, but it's carbon negative. Means there is a less emission, there is a more sequestration. But with the fossil fuels, we have a carbon positive. Means more emission than sequestration. Now biochar and the soil microbes. We know there is a lot of interactions with the biochar when we apply to the soil. Soil, there is a good place for microbial inhabitants, and then microbes can have a habitat in the biochar. But of course, biochar is not a good source of nutrients. It's a source of carbon. It's a good source of aromatic carbons. So it has porous structure, highly surface area, it's like a charcoal, and it has a very good water holding capacity. It's a very good amendment for the problematic soil, like acid soils. In acid soils, we usually give lime, but biochar can act as a liming material. Usually, when we produce biochar, they have a lot of ash content. These ashes can act as a lime, and it can have the correction in the pH. Other than that, biochar can also help for the degradation of the contaminants with the microbes. Biochar and the pollutants, we know there are a lot of interactions with the pollutants having with the biochars. So it can be organic pollutant interactions, it can be inorganic pollutant interactions, and it can be also interaction with the emerging pollutants, like, for example, pharmaceutical compounds, endocrine disruptor compounds. And then they have a transfer of electrons. Biochar can act as an electron acceptor and electron donor complex with a lot of other organic contaminants. As I mentioned, that also we are producing biochar from the pine needles in the Himalayan region. So to sustain the concept of waste mass valorization, this is the main prime concept. So waste to wealth. So we can produce biochar. So there is a win-win-win strategy, because it can help to reduce, it will help the utilization of the local material. It can help to abatement of the pollution from the pharmaceutical waste, and it can act as a potential source for the local material or youth employment, and it can help in the livelihood generation and that will sustain with the concept of self-reliant India of the Atmanirbhar Bharat. So we have produced some biochar from the agricultural waste material and the kitchen waste material, and this work was done with the BIT Misra, and we have published it in the environmental research. So here we see we have produced biochar from wheat straw, rice straw, and the kitchen waste material, and we have produced in the muffle furnace and in the pyrolysis process. And then we can have these biochar materials. You see, we have chosen rice straw because they are in the Indo-Gangetic plains. There is a lot of these rice straw issues, and also and we have checked with this rice straw biochar the removal of the arsenic, because we know in that region arsenic in the Indo-Gangetic plains also a big issue because it's a geogenic contaminant. So you see from here in the left side, we see the same picture of the produced biochar. That's a scanning electron microscope. In the right side, we have given a picture from the FTIR, and this is a XRD where we see the different crystals and with the different peaks and the different elements. So we have studied with the arsenic concentration 8 milligram per liter with the wheat straw biochar, with the rice straw biochar, and with the kitchen waste biochar that was produced at 500 degrees centigrade. And we see the removal efficiency. We can see with the different contact time. So we see the good result nearly at 1 hour in the laboratory study and in the temperature range at 25 degrees centigrade. And we have compared with the different other adsorbent, and as the Honorable Chairperson asked in the previous speaker about the surface area. So we know that surface area plays a big role for any adsorption study for any with any carbonaceous material. So we have done this also surface area study measurement, and we see the arsenic removal, and we see, except for the perilla leaf here in the table that produces 700 degrees centigrade, but we see that almost our compound wheat straw, rice straw, and kitchen waste biochar has very good removal efficiency and also adsorption capacity. And when we talk about the functional groups, biochars is also, and they have a carboxylic group, phenolic group, hydroxyl group. These functional groups acts as a source for the electron transport, and they act with the lignin, cellulose, and then it helps in the removal of the metals, heavy metalloids, and also other organic contaminants with the different processes like electrostatic attraction, precipitation, exchange transfer complex, and there are a lot of the other reactions. Recently, I have completed one project with the Lancashire University, UK, where I have taken the tackling pharmaceutical care products pollutant in the northwestern Himalayan region. As I mentioned, there we have studied and monitored the antibiotic compounds, norfloxacin, ciprofloxacin, in the surface water that were coming from the pharmaceutical waste, and you see the concentration we found almost more than 250 ppb. So that's why I was telling that in the pharmaceutical waste they are dumping in the water without any regulations. So we have found that the different contaminants in the region that was with the pharmaceutical waste. Now my master students, they are working on the biochar, and they are doing the field applications of biochar, and they are studying the effect of biochar on the growth and yield of wheat and mustards, and they are looking what's the soil fertility parameters. Also, they are looking what's the soil microbial respiration study, how the microbial respiration will work. And also my PhD student, she is working on the pharmaceutical removals with this biochar, and how this biochar is helpful in the removal of the contaminants, and what's the exact mechanisms behind it. And I am happy to inform, recently I have received 50 lakhs project from DST SERB for doing further research on the contaminants and the biochar and what's the removal aspects. So I am thankful to DST Government of India, SERB, for giving me this grant. But study is not complete here. It's a small aspects of my lot of study. More have to do. First, we have to look at the economics of the biochar. What's the cost effectiveness? When we go to the people, we have to tell them why you use it. What's the cost effectiveness? So now we are in the process of cost calculation. What's the life cycle assessment? As mentioned by Professor Dubey, it is exactly correct that when we talk about any waste management, we should look for the life cycle assessment, and we should look at what we are putting and what we are getting out. And also the large scale analysis and training workshop, we are also reaching to the local Himalayan people, local Himalayan rural people, and we are trying to motivate them to utilize the pine noodles for the biochar production so that they can use it for the future. So these are some of my publications or citations along with my students and along with my collaborators. So from where this all information taken. Last but not the least, I am very much thankful to the organizer for inviting me and for giving me such opportunity to have such talk. And I am thankful to my chancellor, vice chancellor, dean, my department, my students, collaborator, and of course my family, who were always inspiring me and motivating me to do my work. Thank you. And I want to say that in this year in the World Environment, this was the theme ecosystem restoration. So we can say that biochar can be used as a good tool for ecosystem restoration and also ecosystem maintenance. Thank you for your patience. I'd be happy to have your questions, comments, and suggestions. Thank you. Also, as one of the yes. At least at this scale, we have used removal of arsenic from water and also soil. We have seen that. So actually, we have used 100 ppm concentration maximum. Although we know WHO limit is 10 ppm. Sorry, 10 ppb. So we have used the maximum 100 ppb and also 50 ppb, and we have found almost removal efficiency in the range of 60 to 70%. It's of course it varies, or it depends on from which region you are. But as per WHO limit, it should not be more than 10 ppb. But in some instances, it can be 50 ppb, and it can be 100 ppb also. We have found in the solution. From the West Bengal region, and also we have some samples from the Assam, because in that Brahmaputra Delta, Assam, also they are very highly contaminated with the arsenic. Yes, that's we call it. No. We have taken from the borewell. Yes. West Bengal, Assam, and also some parts of Bihar, they have this. Yes. Thank you. Thank you. Yes, sir.
Biochar can be invested to existing or any existing chemical. That means we need to have a extensive biological culture.
Yes, sir. No, sir. My master students are working on this effect of biochar on the and they are using field application for the growth of wheat and mustard. Actually, we are applying at the rate of 5 to 10 ton per day. 5 to 10.
That my master students are working on. That they are working on at the moment. Yes, we are doing, and we have the different experiments. One with the conventional fertilizer NPK, and another with the biochar. Exactly. Yes. No, that we are doing, and I think very soon we will. Yes. Exactly. Yes, yes, that you. No, actually, the problem is in urea, you get subsidy. Yes. But exactly. But I think we have to convince them that biochar is not a fertilizer; it is rather is soil amendment. The soil amendment. Yes. 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 Yes, that we are doing in the field scale. Yes, now my students are working on this conventional fertilizer versus biochar versus compost. So now we can have a picture. Top gram method is also there for biochar. And now the energy rate is how much energy rate is current energy rate. So that you have to be the exactly. Yes. Yes, that's why I think it is important to do the LCA. Yes. Yes. Thank you, sir.
Thank you, Dr. Mukherjee, for a very detailed presentation. I would now request Dr. Archana Singh from Amity University to deliver her presentation on an economical approach for the treatment of pulp and paper mill effluent system using microbes and fly ash nanoparticles to achieve minimum zero waste discharge. Dr. Archana Singh is currently associated with Amity University as a professor. Her research interests include development of chromatographic packaging material for metal pre-concentration from wastewater, bioremediation, biosorption processes, and hydrogen synthesis for microbial immobilization. With this brief introduction, I will invite ma'am for her presentation.
Good morning. Good morning, one and all present here. So since morning, we have been talking on the utilization of carbonaceous waste material for the bioremediation of wastewater. So my topic is also on the same concept. My talk is on the development of an economic approach for the treatment of pulp and paper mill effluent using nano fly ash and microbial consortium with the aim to achieve the minimum or zero waste discharge. So here I'm not going to talk much about the scenario of pulp and paper industries in India, but it is a well-known fact that it produces huge amount of wastewater and which consists of it contains organic and inorganic pollutants, namely cellulose biomass, lignin, phenols, resin acids, and which enhances its BOD and COD and suspended particles. And if we release it in the environment without treatment or partial treatment, after the partial treatment, it not only harms or not only imparts that toxic effect to the living aquatic system or to the human beings also. So it is very much required to treat it before discharge into the environment. And we know that there are lots of techniques have been developed for the treatment of wastewater, but they usually suffers with the limitation of non-economic or costly, or it may be produces, after the treatment, it produces a huge quantity of sludge. So in the present work, we have attempted to produce a low-cost treatment technology for the treatment of industrial effluent. So this is in the present work is the integrated approach where we have used nano fly ash. Though the fly ash has been used since ages for the treatment of wastewater, but no one has till date used nano-sized fly ash for the treatment of the effluent. So here we have used fly ash as an adsorbent, and then after the treated water with the fly ash, they are subjected for the microbial treatment. So basically, this work involves, or this treatment process involves two steps. In the first step, the water, the paper meal effluent is going to treat with the nano-sized fly ash, and then it would be treated with the microbial consortium. So the fly ash we have collected from the NTPC Dadri. This is the coal-based thermal power station situated in the Dadri Gautam Budh Nagar, and we have used it without any pre-treatment, just to avoid the excess use of the chemical. And we have prepared this fly ash, we further use for the preparation of nano-sized fly ash by ball mill techniques. And not only the fly ash collected from the coal power station we have also checked the remediation efficiency of other fly ash also, which is from the rice husk ash and its nano size. So here, this is the SEM images of nano fly ash, coal nano fly ash and rice husk ash. So coal fly ash is spherical in nature, whereas the second one, which is the rice husk ash, it is a little bit fibrous. And if we compare the physicochemical properties of the coal fly ash and its nano size particle, there is not much difference, only the difference in their sizes. So first, we have optimized the experimental parameters by using the batch studies. And here the parameters were optimized with respect to the adsorbent dose of the nanofly ash, with respect to the contact time, and with respect to the oscillation frequency. So here we can see that out of all the fly ashes like coal fly ash, nano-sized rice husk ash, or mount ash, or rice husk nano-size, the best performance was given by the coal fly ash, nano coal fly ash. So nano definitely, because of the larger surface area, it has shown the highest absorption efficiency as compared to rest of the fly ashes. And after optimization, we have obtained 60 gram per liter of the adsorbent dose and 60 minutes of the contact time, and it has shown maximum efficiency at 80 RPM oscillation rate. So this is the table which shows the reduction in the pollution parameters of the treated and before treated water, and the maximum performance, as I told you, was shown by the nano fly ash. And here the pH level, permissible limit is given. And if we compare the treated water by the nano fly ash, it will reduce, it has reduced, drastically reduced all the parameters before below the permissible limit. And right hand side, you can see the transparency of the treated water. Earlier, it was dark brown in color, and it becomes transparent after the treatment of fly ash. So this nano fly ash has reduced all the parameters, all the pollutant parameters around 85 to 88%. So after the treatment, and once we get the optimization parameters, then the treated water was subjected for the microbial consortium. And for that, we have selected some microbes, some indigenous microbes that were isolated from the effluent itself. So that is why they are indigenous microbes, I told you. Around 94 bacterial colonies were isolated, and they were subjected for the biochemical test. They are subjected for the lignolytic degradation. We have also seen their lignolytic degradation efficiency. And finally, the bacterial consortium were made. And the basis for the formulation of this consortium is their response towards their biochemical test, and their lignin degradation efficiency, and their growth in the effluent medium, and how efficiently it has reduced the BOD, COD, and obviously increases the DO or the color removal efficiency. So on that basis, this is the isolation, these pictures, and this is the test, biochemical test, which we have performed. And some bacteria out of 93 have shown a good result for all the biochemical tests. Some have shown the negative results. So those who have shown the best results, we have selected. And further, this is the slide which shows their lignin degradation efficiency. And finally, they are all grown, all the isolate 93 bacteria were grown in the effluent. And we have checked their degradation efficiency with respect to BOD, COD. And we have, on that basis, we have selected 4 bacteria for the fabrication or for the formulation of the consortium: PP9, PP14, PP38, PP50. And after 24, when we use this formulation for the treatment of effluent, paper mill effluent, we have found that after 24 hours, about 30% reduction in all the parameters were achieved. So the optimum condition which we have attained with nanofly ash, contact time is 60 minutes, adsorbent dose is 60 gram per liter, oscillation is intensity 80 RPM. And with this 85 to 80% reduction in all the parameters have been achieved. And the bacterial consortium that show 30 to 35%. So here we are trying to build a bioreactor. The fabrication process design has been approved. The fabrication process is under the progress. So here we will use both the techniques together to treat the paper mill effluent. In here you can see there are 2 chambers. One chamber would be for keeping our nanofly ash and all the that will work under all the optimum operational parameters. And the second chamber, we will use this chamber. This chamber will be used for the microbial consortium. So this work is under the progress. And after the treatment, we have also checked the quality of the treated water, whether they would be used for the agriculture purpose or not. For that, we have checked its cytogenotoxicity. So the mung bean, or that is also called as Vigna radiata, we have grown some seeds of Vigna radiata in 3 different type of effluents, raw effluent, treated effluent, and in distilled water. And the results which we have found with the treated water and the distilled water, they are at par with each other. And likewise, we have also checked the degradation in the DNA, that is the genetic material. So the untreated water damaged DNA a lot as compared to the treated water. There is very small tail we have found in the treated water, so which suggests that it can be utilized for the agriculture purpose. Likewise, one more test we have done with the treated water, the untreated water with respect to control, where tomato plants have been grown, and the results of the treated water is as compared with the untreated water are far, far better, and results are at par with the control one. So now finally, after the big problem is, after the treatment, the technologies produces a lots of sludge. So here the sludge, after the treatment, the sludge which would be of fly ash and the bacterial consortium, we have utilized in the fabrication of bricks. So different proportionate, we have mixed it in different proportionate, like we have prepared a brick of 100% using 100% clay, second 85% clay and 15% spent fly ash, and the third one where 50% spent fly ash mixed with 70% of the clay. And the quality of the bricks which we fabricated, that are comparable with the standard bricks, 100% bricks. So we can use it for the formulation of the bricks as well, for the fabrication of the bricks as well. So now the conclusion is, with the help of this two-step treatment process, a successful treatment can be done, and 86 to 80% color removal can be achieved only with the help of nanofly ash, and rest polishing can be done with the suggested bacterial consortium. And the results shows that it can be used, though it is very limited study, but it can be used for the agriculture purpose. And the remaining sludge, the sludge which we will be obtained after the treatment process, can be successfully utilized for the manufacturing of bricks. Thank you. If you have any question, I will.
I would request the participants who have joined online, if they have any questions, they can just raise their hands and we can take.
There's lots of parameters have been checked. Here you can see. Electrical conductivity, pH, total suspended solid, total dissolved solid, BOD, COD, dissolved oxygen, chloride, AOX content, sulfate, phosphate, everything. Metals, we have checked for the arsenic, and arsenic, we have checked only for the arsenic, and it also reduced. The size nano, it is around 1 to 50. That is lying because after a billing process, like 80% will below the 1 nanometer of size. We can regenerate it, but here I have not considered that part. Basically, we have utilized that used or spent fly ash in the manufacturing of bricks. Yes, we have also checked that. That is the biodegradation process. Biodegradation. It secretes several enzymes. This consortia secretes several enzymes which breaks the this lignin and cellulose material. No bacteria is there. Even there is no if we we have also checked the leaching of heavy metals, so we have also not found that, because during the manufacturing of bricks like they are all vanished. Heat normal heat baking. Mostly they are all bacillus, and one new species we have obtained, that is Bacillus pseudomycoides. So it is, it is relatively a new microbe, and its efficiency, removal efficiency is very high. 16 sRNA. No, we have outsourced. Sorry? Leaching of, not micros, leaching of heavy metals. That is in lab scale only. Okay, thank you. Nanoscience. Yes. Rate of reaction, we have like you were talking about this first order of reaction. Like with time, with time which would act faster. Do you want to ask that? Yes. This absorb faster. Nanofly absorb faster as compared to that. Yes. Like nanofly at 85% to 88%, whereas the other one, the core one, like the raw material, that show around 60 to 65%. What is the proper rice has also show good efficiency, but the problem with rice has is that it floats. It is difficult to settle it down after the treatment. I'm not going. We are not mixing it together. We are individually using it for the treatment process. No. First, we have checked the performance of all the fly ashes individually, and then we have obtained that the performance of one fly ash is far better than the rest of the fly ash. So we selected that, and in the next step, we have utilized formulated consortium for the treatment. So once the effluent get treated with the nanofly ash, that because it is going to treat only 85%. It is going to reduce the pollutant parameters up to 88 or 85%. Rest part is going to be treated by this microbial. No, not. We are not mixing it. We are doing it individually. Just compare the performance. Just to, we have used it individually and we have compared their performances against the treatment of the different institutes. Okay, thank you. Thank you. They are involved.
We can take this offline in the networking session. There are other people waiting. Yeah. Thank you so much, ma'am, for your insightful session today. So our next keynote speaker is Dr. Smita Mohanty from CIPET LARMP. So I would request Aryan to give a brief introduction and move along with the session.
Thank you, Ria. Dr. Smita, ma'am, are you there in the meeting?
Yes, I'm there.
Yeah. So hello, ma'am. A very good morning. Just to brief about Dr. Smita, she is currently based on RPM CIPET Bhubaneswar. She has extensive experience in polymer composites, plastic waste, and biopolymers. Currently, she is heading CIPET SARP-LARPM in the capacity of director and head principal scientist. Her research area includes composite nanocomposites, plastic waste management, and recycling biopolymers. Today, ma'am will be talking about single-use plastics, opportunities, and challenges. With this, I welcome you, ma'am, to this session.
Thank you so much. I'll just share my screen.
Sure, ma'am.
Is it visible?
Yes, ma'am, it's visible. If you can put it in a full screen mode.
F5 mode. Okay. 1 second. It's fine now?
Yes, ma'am. Yes.
Okay. Okay.
Please continue.
Thank you so much. Now, at the outset, I would like to thank all the organizers for giving me an opportunity to speak. This is actually one of the most emerging topics, single-use plastics. I think everybody is, now and then talking about what are these single-use plastics and what are the opportunities and challenges we come across. Now, if you see the plastics, if you see the scenario, it's a very versatile material. But unfortunately, what we see in the litter, that is only being blamed. Today, if someone of you, if you ask me what is plastic, then if as per a layman's version, it is a bucket, it is a carry bag, that's it. But actually, if you see, plastic has got a plethora of applications. It is widely used in transportation sector. Today, when you come across for fuel efficient vehicles, car components, all these are made out of plastics actually. Apart from that, there are huge applications concerning to your healthcare, agriculture, energy harvesting systems, as well as packaging systems. Now, in healthcare, as all of us are aware that during the COVID-19 pandemic, the plastics were actually a saver because entire PPE kit, your cartridges, lot of things, your blood bags, other things can be, you can see the application of plastics over there. So these are all lightweight, cost effective, easy availability, processing, corrosion resistance, and sustainable as well. Now, how it is that? Now, if you see the sector-wise consumption as per the Indian scenario, I have taken one statistics of what are the different categories of plastics which are available and what is the consumption of the plastics which are available. So basically, we classify these as two categories. One is the thermoplastics, other one is your thermo settings. Based on that, we come across the different share of plastic consumption in different sectors. Like for example, we have packaging sector, which is normally your carry bags, then your atta packaging or your Maggi packaging or whatever, those things, those items you call it as your packaging sector. Now that constitutes of about 43%. Apart from that, we have also infrastructure sector, which is 21%. We have automotive sector, which is 16%. We have other sectors like we have electronics and electrical and electronics. We have building and construction. And apart from that, agriculture, which has now been increased to, it was hardly 2%, but now currently it has come over to 5%. But at the end of the day, if you see, the packaging sector has been grown abnormally, you can say exponentially, from 22% to 25%. Now it is 43% of the total consumption is approximately near about 50%. It is approximately your packaging sector. Now, if you see, what is the per capita consumption of plastics in India? If you compare vis-a-vis the global usage, India is much less actually. The per capita consumption, per person consumption, it's 16 kg per person actually. If you see the data as per statistics as per 2020. And whereas in all the developed countries, it is 109 in US, Europe, it is 65 kg per person. China, it is 38 kg per person, almost our double, more than double. In fact, Brazil, it's 32 kg per person. So we are far less as vis-a-vis the other parts of the world, but still plastics are being blamed. Now, why that happens? Let's go now to the major things. Number one, what are these single-use plastics actually? And what are these single-use plastic products? What are the concerns? Now, if you see the plastic carry bags for vegetables, groceries, food parcel services, etc., whatever that is being irresponsibly littered directly into the environment or are disposed of by the collectors in the landfill, those things are basically your single-use plastics. Why they are to be blamed? Because plastics are durable, they are sustainable, they take millions of years to degrade. So that is why they tend to remain in the environment for decades together. And that has been a great concern. It has been a great global concern because the land-based resources, whatever we litter it, whatever we throw it in the environment, ultimately it migrates into your marine food chain and it affects the marine food chain. And it chokes the animals and birds to death while polluting the oceans and environment. So that is why these single-use plastic products, or we call it as soups, these are basically because of our littering habits, because of our irresponsible waste management which we have. So that is why these plastics, they enter into the act as substrate, and they can be a major carrier for persistent organic pollutants, or whatever you may say today, polluting the oceans and the other aquatic food chain, you can say. Now, as per the categories, as you can see in the left hand side of my slide, we have a recycling code, the type of plastics based on the recycling code, and there are the based on different types of plastics, we classify them as which are the safest choice, which are the safe choice, which are you need to avoid them. Based on that, if you see PET is called as your safe choice. Normally, if you see a water bottle today, those are made out of basically the polyethylene terephthalate. Now, why we call it as a safe choice? Because today PET is 100% recyclable. Any kind of sports garments you see, whether it's your sports apparels, your shoes, your t-shirts, or anything of that sort, those are predominantly manufactured from PET. Apart from that, you have high density polyethylene. That means you have milk, detergent bags, the carry bags, containers, etc. We call them as the safest choice because they can be easily recycled. They can put to recycle and value addition, and that is why we call them as a safest choice. Polyvinyl chloride, where you find all your pipes and fittings, that is made out of polyvinyl chloride, your entire floorings, PVC floorings, cables, wires and cable sheets, because of its non-conducting nature, because of its durability, flexibility, they are being amicably used as cables, but we call them as avoid. Because why? Because so far what was happening is that these plastics were incinerated. Because how to dispose of them, dispose of these kind of materials post their service life? So when you are incinerating it, lot of toxic fumes, whether it is dioxins or furans, is being released into the atmosphere. That is why incineration, end of life disposal becomes a problem. But now technology has come up, and some of the technologies are also developed at CIPET. What has happened is that PVC can be amicably, it can be recycled, and it can be value added to different kinds of products. Low density polyethylene, that is recycled code, you have 4. We call them as the safest choice because this can be used as carry bags, films, small bottles, etc., etc., which are found in the litter itself. But they can be recycled, they can be disposed of amicably. Apart from that, there are polypropylene, which is also a safest choice, safe to use. Then you have polystyrene, that is the foam cups, packaging, teacups, ice cream cups. This has been phased out by Government of India because so far the technology for disposal, end of life solution has not come up. Then we have the 7th category, that is others. We call it as a multi-layered plastics, laminated plastics or thermoset plastics. We call them use with caution because some of the multi-layered plastics can be converted to value added to different items or different products, but not all. Because when you have these multi-layer plastics, because of our comforts, like for example, when you pack a biscuit packet, or you have a Lay's namkeen packet, you need the food items to be preserved for a longer duration. So based on that, the packaging is also multi-layered. That means you have dissimilar family of materials. You have a polymer, you also have an adhesive layer in the middle, then you also have a metallized coating just to preserve the food, whatever perishable items you are packing in. So what happens at the end of the day, when we eat it and we dispose of these packets, they are irresponsibly littered in the environment. We do not know how to recycle them because there are dissimilar family of materials. To recycle it and to go for value addition becomes difficult. So that is why we call it as these laminated plastics. Use them with caution. Now, so what are these single-use plastics? We have adopted the definition. If you see during 2018 World Environment Day, when India was a host for World Environment Day, so during that time we had adopted the definition of single-use plastics from UNEP. Essentially, UNEP, UK and EU definition was combined and it was adopted. But fortunately, with the latest plastic waste management rules, our single-use plastic definition are in place now. So we call them as a commodity, which means a plastic items which is intended to be used once for the same purpose before being disposed of or recycled. And if you see, Government of India has listed the products which are categorized under these single-use plastic items, which are environmentally very problematic, and you cannot just use them. And that is why some of the items have been phased out by the Government of India as per the norms, and before 2022 December, we have to phase out amicably these kind of materials. So what are those? These includes your earbuds, then your plastic sticks for balloons, plastic fags, then your candy sticks, your polystyrene thermocol, etc. And also your cups, plates, cutlery, etc., forks, etc. These are also banned. So that is why these single-use plastic items, those which do not have any value addition, have been proposed by the government to ban it or to phase out. Now, this is a study we did it for categorization of the single-use plastic products. What we did is that we had developed a matrix. As you can see here in the left-hand side of my slide, this is a matrix which has been developed for various categories of single-use plastics products. Now, what we have done basically is that what we did, we have taken 5 factors of utility and we have considered 5 factors for adverse environmental impact, adverse impact on the environment. So what are these? What does this means? That means we took hygienity, product safety, essentiality, social impact and economic impact of the plastics when you consider 5 factors of utility. So what are these 5 factors of utility? I'll give just a classical example. Today, if you go for PVC bags, blood bags. So in that PVC blood bags, what happens basically? Now that cannot be replaced because it is hygienic. It is a product safe. It is an essentiality because you cannot use a glass bag. You cannot use a container which constitutes of some other kind of plastic material, because at the end of the day, the blood should retain its purity. So that is why it has been mentioned as a 5 factors of utility. We give them a higher number or a higher marks. Similarly, if I take a small tiny chocolate wrapper, what happens? You take the chocolate, you eat the chocolate, you dispose of that wrapper, you throw that wrapper. So the rag picker will never come and collect that wrapper because it is such a tiny thing. It is being littered everywhere in the environment. So that has been considered based on the collectability, recyclability, end of life solutions possibility, impact on alternate materials, and your littering propensity. So if you see in the litter, maximum number of, you can see your chocolate wrappers are being thrown away. So they cannot be collected. So they are environmentally problematic. So based on these utility, we classified these products, these categories of single-use plastic products, which has got environmental implications, direct impact on the environment. For example, thin carry bags below 50 microns. That means what happens? The strength of these carry bags are such less that that it is evident in the litter. Everything is literally found in the litter. Then you have small wrapping or packaging films, your cutlery or your foamed cups, then your laminated bowls, cigarette butts, small plastic bottles which are less than 200 ml, expanded polystyrene, straws and stirrers, non-woven carry bags. So these are some of the items we decided. We had done the survey. We have classified based on the utility, and that is why they are considered as the environmentally problematic. Now, so what is the reason to refuse these kind of single-use plastics? Number one, first is these are made from fossil fuel. It has got huge carbon footprint, prolonged exposure to 100 years, and then percentage, very small percentage is being recycled, leaches toxins. See, I'll tell you one thing, why it leaches toxins, because plastic itself acts as a substrate. When you add any chemicals in the environment, that sticks to the over the surface of the plastics. Again, during the processing of the plastics, because of our comfort, because we want certain kinds of properties or the parameters, we add some additives during the processing. So that is why at the end of the life, when it is disposed of or when it is found in the environment, it is littered, these kind of toxins are released into the environment. Causes hormone disruption and cancer. This is yet to be established, pollutes the oceans, kills the marine animals, and then enters in the food chain. So these are the primary causes why we need to refuse the single-use plastics. Then if you see the statistics, it is 100,000, you can say, crore industry with 13.4 million metric tons, growing at the rate of 10.5% CAGR. And if you see the strength, we have 50,000 active processor, 7,500 recyclers, and disposal is hardly 60%. So whatever is disposed of, this 60% is because of your PET bottles, because it is 100% recyclable, and we have in our country amicable recycling technology, and incentives are also provided. What are the methods to cut these single-use plastics use? You can cut your eco-friendly cutlery, you can adopt it. There has to be some waste collection and recycling. Innovation in the packaging material which needs to be arrived, which I'll show in my later slides what we have done basically. Then eliminating bottles and refill stations. Biodegradable polymers, which is a recent one, which people have been talking about it since I think more than a decade, but technology pertaining to it has not been established because of manifold reasons, starting from cost effectiveness to the processability during its operation. And straws, irrespective of straws, we can adopt something else which can be, so straws can be also, we can say no to the straws. These are some of the methods which have been listed to cut the single-use plastic use. Now let's see what are the alternative products. You can see bamboo-based utensils. These are very much evident in the airports where you will find, a lot of materials, bamboo-based cutlery has come, a lot of things have come. Beeswax food wrap. I'll show you some of the application what we developed. Then stainless steel straws can be adopted. Reusable coffee filters can be adopted. Sustainable sponges can be adopted. So these are some of the things which you can go for alternatives to single-use plastics. There are also some eco-friendly materials to replace the single-use plastic products. Some of them are starch-based blends. You have polylactic acid-based blends, bioplastics made from thermoplastically modified starch, bioplastics made from PLA. Then we have cellulose-based plastics, bio-based plastics or bioplastics, that is your bio-PE or bio-PET. That means when you are sourcing out the raw material from any kind of renewable resource-based material. So these are some of the eco-friendly material to substitute the single-use plastics. Now, I'll just give you a brief about what exactly we have done. Some of the research activities we have also done using these biopolymers. Some of the field trials also we have undertaken. I'll tell you what are the things which we have noticed. If you look at the impediments in biopolymers, what are the major impediments? Number one, the mechanical strength is very poor. Thermal stability is limited. So during processing, it has got a major difficulty. And one of the most targeted thing, which today also we are facing it, that is high cost. If you see the normal polyolefins or your polyethylenes, the cost is hardly 160 rupees per kg. But if you compare vis-a-vis your PLA or PHB or PBAT or any kind of those kind of polymers, the cost is 370 to 450 rupees per kg. So that is why the cost is exorbitantly high. And apart from that, we also face various kinds of technicality, like it becomes difficult to process. The properties are also not at par with the normally or conventionally applied polyolefins or whatever systems you are noticing it. Now let's see. So these are the weaknesses. like sensitive to moisture in the standard form, poor interaction with the fillers or any additives which you add during the processing. There is a very narrow processing window. I mean, it needs to be processed within that temperature parameter and within that RPM. Otherwise, what happens is that normally the processability, it becomes flows like water. Lack of reactive groups, thermal degradation, and brittleness. So these were our targeted properties. That is mechanical strength, we need to enhance it. Sealability, we need to enhance it. Permeability as regards to OTR, oxygen transmission rate, or water vapor transmission rate, and processability, flexibility, anti-slip property. These are some of the parameters which we need to address during processing of any kind of biopolymers, whether it is PLA, polylactic acid, or PBAT, that is polybutylene adipate co-terephthalate, or PHB, whatever the normal thing which we come across. Now, during the polymer formulation developed, what we did is that we tried to modify the interface of PLA or PBAT with different categories of nanoparticles, with starch, then varieties of thermoplastic matrix, and the concentration of the nanoclays. We modified the surface and we tried to develop the interface also between the resin and the resin as well as the filler. So what we did, this is a film, what you can see here. This is a PLA with a starch. Why we had developed that PLA and starch? Because starch is, as you all of us know, that it is quite abundantly available in India. And normally starch, you can get corn starch, you can get potato starch, you can get maize starch. So a lot of starch varieties are available in India. It is quite cheap also. So what we did, instead of taking PLA as a whole, we tried to modify the interface between PLA and starch. And as such, starch cannot be used as a filler inside the polymer matrix. You need to thermoplasticize the starch with any kind of glycerol and water combination or anything. Then after that, you have to process it with any kind of biopolymer. Again, the polymerization, when you do processing, at that time, we need to add several additives, including your initiator or your, glycidyl methyl acrylate we have added. We have taken it as, compatibilizer. To chain extender also you can add, so that some sort of flexibility is developed and the film properties which is required, that is being maintained. This is what we have taken the, you can see here, this is a scanning electron microscopy of starch, different levels of starch, and how we have done and what way we have processed it. Like here you can see in the second and the third slide, there are a lot of agglomeration. This is the second slide, this is the third slide, and this is the fourth one. So in all of this, as you can see here, what we have done, we have tried to load starch as such, 5%, 10%, 20%, 30%. So this is 5, 10, 20, and 30. As you can see here, there is a lot of agglomeration of starch. So what happens, the interface compatibility is relatively less, and that is where the film fails. Subsequently, what we did, we modified the interface between the starch and the PLA matrix. So accordingly, you can see, as you can see, some sort of modification happens. What we did is that we did the grafting of PLA, and as well as glycidyl methacrylate, we have taken it and we have added it as a compatibilizer. And at the same time, we grafted it with PLA so that some sort of compatibility between your PLA as well as the starch matrix developed. Now, this is a AFM I have taken, wherein you can see the roughness. Now, as you increase the amount of your, as you increase the amount of your starch loading, again, the roughness increases. So that means that some sort of compatibility, there is some sort of heterogeneous mix is obtained, and that is where it fails. Now, this is an open field trial which we have taken. As you can see, the mulches. These are all organic mulches, and then your plastic mulches also. So in case of the organic mulches, what happens is that dry leaves, paddy straw, sugarcane molasses, these are being taken. Plastic mulches, they serve better than the organic mulches because they allow the plant to grow without any weeds or other things, and it is completely impermeable to water. So these are some of the PLA based films which we developed, and as you can see, with different compositions of different loading of starches we have taken and we have optimized it. And this is how we have done the optimization of different categories of films, blown films out of it. Now this is the field trials which we have taken, and as you can see here, based on that, what we concluded, our basic conclusion is that after the film is degraded, then when the next crop cycle is, sorry?
I'm sorry to interrupt, but due to time constraints, I would request you to
I'll take another 5 minutes. I'll take another 5 minutes.
Okay.
So what was the observation here is that after the next field trials, what happens? Whether it is impacting these kind of biopolymer based mulches, as such we didn't observe any negative impact on the growth of the plant. But after it is being after this starch films are basically it has gone, what happens to the compost? So what we did, we did the complete characterization of your aerobic biodegradation. What we noticed is that these kind of films are completely sustainable, and we could notice that they are completely biodegradable. We did the complete heavy metal analysis because we are also adding some kind of some nano fillers and other fillers to compatibilize the system and additives, but it was within the tolerant limit. Then this is another thing which I will just give a brief. This is a patented one which we have developed. That is a biodegradable sanitary napkins. Now, instead of going for polyethylene and polypropylene based polymers, sanitary napkins, that everybody knows that we have got 3 layers. So what we did is that one layer we have substituted with a biopolymer, and the inner core layer we have sourced out the cotton from Kalahandi districts, from the tribal district of Odisha. We have modified that cotton, and some of the sap particles also we took it from your wheat gluten as one of the sap particles. So that wheat gluten was again modified with a dimer acid hydrogenated, Prepol 1009 we call it, and then bio-based super absorbent was derived. What we did is that we tried to see what happens, whether there is any fungal growth or something. So we did the biodegradability condition also, we evaluated it. We could find that the treated wheat gluten did not show any kind of fungal growth. So this was the absorbent core, as you can see here, raw cotton and the modified cotton. This was the absorbent core which was developed, and we did a complete comparison with the conventionally available, commercially available napkins which is available, and we could find the properties at par. So this is how the top sheet also we are fabricating now with PHB based. Then some of the other packaging also we developed. These are for the edible food packaging which we developed it, where the barrier properties and other things are also maintained. This is basically PLA with PBSA and other kind of ESA based systems. So these are some of the studies which we have done, and some of the comparative account which we have shown. So these are some of the value addition, as you can see here, which is readily available in India. Like from PET bottles, you can go for apparels, milk pouches to Barsati films, then oven sacks to Nivar patti, then all your battery cases to luggage, then plastic carry bags to mats, and PVC pipes to shoes. So these are some of the global developments which are the paper-based. As you can see, the paper-based cups have come up, then your paper-based tubings have come up, then board toppers, then some of the plant materials like Dell has partly replaced with EPS, then cardboard box, it has come up, straws have come up, then coatings with that mimic the fruit skins, that has also come up, and some of the edible wrapping paper, cutlery items. So I will end my talk here. Thank you.
Thank you so much. Thank you so much, ma'am, for this presentation. Now I would request our chairperson and co-chairperson, if they have any further comments on this, then they can kindly ask. Request the participants if they have any questions, maybe online or offline. No. So with this, I thank you so much, ma'am, for this presentation. And now moving ahead, I would request the dignitaries, the keynote speakers to please be there on the stage so that we can felicitate you. I'd request the chairperson and the co-chairperson to kindly felicitate our speakers. Dr. Shantanu and Dr. Rachna, please. With this, I would take this privilege to thank our rest of the keynote speakers who couldn't join us today. Dr. Brajesh Dubey, Dr. Popita Das, and Dr. Smita Mohanty for their talk. And just for the information, we will take Dr. Neha Singh's talk after the tea break, the tea session. Please, sir. I'd request Prashant sir to please be on the stage.
I think there is some question. Somebody has raised the, maybe I can, he's asking to unmute. There are some questions, Prashantji, if somebody desires, maybe I can answer this since it is a tea break.
Now I request Prashant sir to please felicitate our chairperson and co-chairperson. Thank you so much, everyone. Now we will break for a short tea break, and then we can assemble at around 12:30 sharp.
I think there are some questions.
Request everyone to please be here by 12:30. We will start our 4 technical sessions sharp at 12:30. Thank you. The tea is outside. Please have it. Thank you.
I think there are few questions. কি আসছেন রে হ্যাঁ ডাকিলে কোন হলো কাই আসছেন তো ଆପଣ ଏଇ ଯୋଉ କ୍ୱାଲିଫାଇ କରିଛନ୍ତି ବୋଧେ जो PhD एंट्रेंस टेस्ट राइट हाँ हमें अच्छा कुछ लोग क्वेश्चंस के लिए हाथ रेज किए हैं तो कैन यू
I can see few of the hands in the chat box, so we can have the questions. Dr. Pirzada, if you are there online, then you can ask a question from Dr. Smita. Smita ma'am, you there?
Yes, I'm there. Yes.
Yeah, okay. So I request the participants, like if they have the questions, they can unmute themselves and they can ask.
Hello.
Yes, sir. Yes, sir. Please.
Good afternoon, madam.
Good afternoon.
Myself, madam, Dr. Manmohan Bagh. Hello.
Yes, yes, yes. Yes, please.
Hello. Myself, Dr. Manmohan Bagh, madam. Hello.
Yes, sir. You are audible. You are audible.
Since 5 years, madam, I am working on the recycling of plastic in field level.
Okay.
In my experience, madam, there is a no provision for single-use plastic.
There is no provision for.
So we cannot hear you.
Hello.
Ma'am, we can take the next question from Dr.
Hello.
Ma'am, we can take the next question.
Ha.
Dr. Yasir.
Please unmute yourself. He is not able to unmute.
Yeah, good afternoon, ma'am.
Yeah.
Actually, I have a question regarding the processing of the material. If we want to change the organic material into the plastics, then during processing, is there any negative impact on the environment?
That's what we are doing. We are doing the field trials as well, because starch we have added just to see that the cost effectiveness, but at the same time processing of PLA, I tell you, is one of the Herculean tasks, because it flows like water. You have a very narrow processing window. So what we did is that we added some PBAT also into it, but very less quantity PBAT, because PBAT is 410 rupees per kg. We added starch also to it. And then what we did is that we first of all thermoplasticized the starch. We added the compatibilizer, that is glyceryl methacrylate we have taken. And at the same time, you can take any kind of initiator. And then you fabricate. The films have come out very nicely. The problem is that what has happened is that now we are in the verge of second cycle study. We have laid it on the field. It's a complete field trial, which I showed you in the mulching trial. First cycle, the crop growth, everything was perfectly okay. There was no weed growth. The crop growth also was good. Everything was good. Then after the UV degradation, what has happened is that it has turned to be very brittle, because it's a biopolymer, and at the same time you are adding organic thing into it. So anyways, the brittleness will increase. So now it has been converted to a powder form. It has assimilated within the soil. If you go for the test method, test protocol, we followed that whether it is biodegradable or not, it is 100% biodegradable. 92 to 93% biodegradation ratio is there. But next question comes when I go for the next crop cycle. Okay, 6 months is over, one crop cycle is successful. But when I go for the next crop cycle, I am doing the plantation now. So I need to see whether the powder or anything, whatever is assimilated into the soil, it is going to impact the cycle of the crop or not. That is under progress. And maybe in another 3-4 months, by Jan or Feb, we'll come to know the results.
Okay, I think there must be some effect on the carbon, land and water footprint of these bioplastics also.
Yes, yes, yes.
So assessing that point in your study.
Yes. Microplastic formation also we are assessing it. So microplastics, whether there is any formation of, because for us, for a layman's understanding, everything is assimilated into the soil. We call that, as per IS 17088 standardization technique, we call it that it is continuously, it is biodegradable, right? But we don't know where it goes when it is in a mass scale. So that is the thing. The catch is that
Okay, thank you. Thank you for the answers.
Yes,
Next
sir.
we will take Shubham Sai Mahapat. Sir, are you there?
Good afternoon, ma'am.
Yeah, good afternoon.
Actually, I am Soham Mahapatra. I am doing my PhD in NIT Rourkela.
Yes.
I am working on co-pyrolysis of sugarcane bagasse and thermocol waste. Actually, you mentioned about EPS, no? Is it EPS is expanded polystyrene?
Yes,
Is that
it's expanded polystyrene. Yes.
thermocol is a type of expanded polystyrene? Is it like?
It is expanded polystyrene only, thermocol.
Yes, yes. But I wanted to know if we are burning that, means if we are conducting any, we are conducting pyrolysis, is it the gases that are emitted during the course of burning, is it toxic? Means that's what I wanted to know.
That is why government has banned. Because when you are undertaking NEC, if it is a closed system, that is a different story. But if you are incinerating it in an open environment, then it will have impact. It has got negative impact. That is the only thing. But if you are doing a closed loop pyrolysis, I don't think any problem is there. Because now people are telling that EPS can also enter into many kind of, as a fuel generator, or you can say for cement clean plants. But I am not sure about that technique. But we have come for amicable recycling of foams, flexible foams and rigid foams. We are able to recycle it completely now. We are going to recycle. We have established a small lab scale setup of recycling that, chemical recycling. So that aspect we have done it.
Where, ma'am? In CIPET Bhubaneswar?
Yes, sir. In Bhubaneswar, we have set up. So maybe if you want, you can write to us and we will plan a visit for you and you can check up. Flexible foams. It is not polystyrene foams. It is basically your polyurethane. It is polyurethane. Yes.
Okay. No, actually we are working, but is it that we can use any to lessen the effect of toxic effect of that gas? Is there any?
You can go for, see, I have not started any chemical recycling technique. I have not initiated any chemical recycling technique. What we have done, we on a very old patent we have been working, but that patent again we have modified it and we are working on polyurethane flexible foams. So maybe styrofoam also, there are some methods also that we can try out that.
No, you are doing that recycling, means like pyrolysis and all.
No, pyrolysis we don't do. Ours is basically either it is mechanical recycling and chemical recycling, partly we have set up.
More specific, means chemical recycling means what kind of?
Chemical recycling of your polyurethane foams. Especially your polyurethane foams. That is through solvent method, we are extracting it and end of the day, we are converting it into the monomers. Okay, it's a polyol and an isocyanate. So polyol, we are converting the polyurethane to polyol. That polyol purity and other things we are checking now. It's a mixed polyol.
Thank you, ma'am.
Thank you.
Next, we have is Mohan Bag.
Hello.
So you can ask a question.
Madam, I am working. Hello.
Yes, sir. Please tell me.
I am working the recycling of plastic, madam, since 5 years. What in my field experience, the thermocol are the one of the most dangerous thing. Those are polluting the environment. So what step can be taken, madam?
Thermocol they have banned, na sir. The step is simple step is thermocol they have banned because there is no alternatives to that. Number one, there is no end of life disposal to that. So that is why thermocol they have banned.
But
that's what the previous questioner he was asking. The styrofoam and yes.
in the field level, madam, it is not banned and rampantly it is used.
December 31st, 2022, they have given a target. If you see, MOEF has given a target of banning some of the items. Out of that, thermocol is major is thermocol. So for decoration items also, they have banned now. So now slowly thermocol industry will phase out. I think he has got some problem in his this thing.
Ma'am, we can take his question.
Okay. In case anything is there, then you can write to me, right?
Yeah, ma'am. If they have any questions, then maybe they can post it here itself, or they can write it to you. No problem.
Okay.
Thank you so much, ma'am.
Thank you so much. Thank you. Bye.
Bye, ma'am. Hello everyone, welcome back to the fourth technical session. We will take Dr. Neha Singh now as from the third technical session now. Dr. Neha Singh is an amazing scientist from Banka Bio Limited, and she is currently working on fecal sludge management. Ma'am, I would request you to kindly mute yourself. Dr. Neha, can you hear me? Yeah, hi, Dr. Neha. Ma'am, can we start with the presentation?
Yeah, sure.
Yeah. So I'm sharing it from my end now.
Yeah, I'll share.
Yeah, the presentation is visible, ma'am. You can start the presentation. If you can put it in a full screen mode.
Yeah, sure.
Yeah.
Is it visible? Hello, I'm audible?
Yes, ma'am, it's visible, but it's not in a full screen mode.
I did already showing here up to full screen mode.
Shall I share it from my end, ma'am?
Okay, okay. Shall I start?
Yes, ma'am, please.
First of all, a very good noon to all of you. I hope you all are doing good and fine at your end. So I would like to thank WMSD 2021 for extending this opportunity. So without any further delay, I would like to begin my talk. So today I'm going to talk about fecal sludge management and facilitating resource recovery. So first we're going to talk about septage. As you already know what is septage. In our country, like in Asian countries, most of the remote areas, they don't have centralized system for the seepage treatment. So there they are using septic tank for storing their night soil, or you can say for storing their fecal sludge over a period of time. So septage is generally the fecal sludge which gets accumulated into the septic tank over a period of time. So almost it's get partially digested. In some cases, if you leave it for some like 2-3 years, it will get fully digested. So you can see in this picture there is a vacuum truck, or you, in common language we used to say it as a decanter. It's just like, it works just like your vacuum pump. So it has, with the help of the hose pipe, it used to provide positive and negative pressure. As we know, in septic tank the sewage get used to store it for a long time, so the most of the solid, it used to get settled down at the bottom of the tank, and water at the upper portion, which may go through the overflow to the soak pit. So before collecting the septage, we should make sure that the a suspended solid which got settled at the bottom of the tank, it get homogenized with the sludge. For that, we used to provide, with the help of the decanter, positive pressure, and it used to take 10 to 15 minutes to all the sludge or all the suspended particles to get homogenized. So after that, with the negative pressure, these septage is getting collected into the decanter. So it can proceed for the further treatment at the FST. Is generally fecal sludge treatment plant. So our company called Banka Bailo, it has FSTP plants from all across the India. I can say we have FSTP plants in 5 regions. We are dominant in Andhra Pradesh, Telangana, and we are extending up to Rajasthan also. So next slide. In this slide, I'm going to explain like how this process flow work in our FSTP plant, how this septage is getting treated in our FSTP plant. So with the help of decanter, the septage used to bought at the FSTP plant, that fecal sludge treatment plant. So this decanter used to decant the septage in the sludge holding tank, but before that it used to get passed through the screening chamber. The screening chamber, it has a mesh size of 8 mm to 10 mm, so it can remove all the inerts like as we humans we used to dispose our loo or night soil. It's not only contain fecal sludge or your water content, it has many inerts also, like your solid inerts, toilet papers, then napkins. So this screen is just to remove those things, and it basically work on the gravity basis. So after that, the sludge used to get stored into the sludge holding tank. In the sludge holding tank, we can store our sludge up to 24 hours also, because as we know, septage, it's in most of the cases it is fully digested. So the biogas potential, I mean the biogas generation is almost nil. So this septage, after getting collected into the sludge holding tank, again it will settle down, because suspended I could say settleable suspended solid has a tendency to settle down within like 1 to 2 minutes. So we have to before processing, our main challenge in septage is to separate the suspended solids from the water. Okay, so so our next step is to homogenize that thing again, like there in septic tank. We homogenize the sample with the help of the sludge, with the help of the decanter, by providing positive pressure. Here we are using submersible cutter pump. With the help of that, we used to homogenize our sample, and even we used to recirculate some of the samples from the Can you go back to the previous slide? So we used to recirculate some of the sludge also from the aeration tank, which gets settled at the bottom. We used to do like this because the septic tank, I mean the septage in the septic tank, it's not necessary that its characteristics like dry solids, which is our main focus or main challenge to reduce, or we can say in common term total solids, it's not going to be constant. So to maintain the constant thing, because we have done many hit and trial methods to, like our next step is flocculation. For flocculating, we need dry solids of particular percentage, like so by hit and trial method, with the polymer which we have used, it basically works with 2 to 12% of dry solids or total solids. So because of that, we are recirculating our sludge in case if our septage has, I mean, very less total solids, less than 2%. In that case, we used to recirculate some of the septage into the, or we can say sludge into the this sludge holding tank. After that, our next step is, as I already said, our major challenge is total solid, suspended or settleable solid. So we have to separate this total suspended solids from the water. So for that, we have solid liquid separation system that is called geotube dewatering system. So the size of the solids are very small. So before separating it, we need to make it like of larger size. So for making it of larger size, we are using polymer that is a medium molecular cationic based biodegradable polymer, which automatically gets degraded after 24 hours. So with the help of that polymer, we used to make flocks of larger size, because the that geotube which we use to separate solid and liquid, it has a mesh size of around 300 microns. So we don't want any particles less than that. So obviously, if it is less than 300 micron, it will get passed through it. So we used to make flock, and this is called this system is called anaconda pipelines, because after making flock, obviously it needs time to make flock. Won't get so easily, so it needs time. So after making flock, it used to get passed through the geotube. In geotube, most of the solids it gets separates from the water. This geotube bag is it's capable of separating if our flock is good, if it is in the percentage of 2 to 12, then automatically our flock will be good. This geotube will separate all the flocks from the water, and it's it has around 99% of capability of separating those flocks from the water. So these flocks, it gets stored into the geotube, and the water we further send it to the aeration tank, or we can say in sequential batch reactor. There, this aeration tank or aeration system, it used to fill up to 2/3 2/3 ratio, and 1/3 ratio we used to provide from the geotube. So this aeration process, it may last for 3 hours for every batch. Actually, we used to run this whole batch for one suppose 10 kl of water, we used to run this whole batch for 7 hours. So after this, after providing aeration, and we have already 2/3 of sludge inside it, so we don't need any extra inoculum to add into this aeration system, because that is sufficient to provide microbes for degrading all the dissolved solids from the septage. So after this, we used to feed the filtrate into the secondary chamber, that is your filter feed tank, and once it's get settled down there, we used to take out the upper layer or the unsettled part, upper layer, and from there we used to pass this effluent to our tertiary treatment, that is which constitute of the following things, like pressurized sand filter, which is very common, and then our activated carbon filter, then micron filter, and then this water used to go through UV disinfection, and then finally we used to store into the treated water tank. In this treated water tank, different there, from there we used to obviously we can't dispose it to the environment, although it met all of the, in most of the cases, about 90% we used to achieve all the effluent characteristics or physicochemical characteristics which is set by CPCB for inland characteristics, but we are not disposing it to the to the river or anything. So we are using this treated water effluent for the green belt development. In our facility only, we use this treated water for gardening or horticulture purpose. So, and in some cases, we used to give this treated water to urban local bodies also. So they use it for gardening and horticulture too. So next. So here you can see this is the image of our geotube or geobag, which contains sludge and slurry. And further, this geotube, after getting trapped the flocks, our biosolids gets trapped into this geotube bag, and once it gets filled, it takes around I mean, it depends upon the amount of sludge we are receiving. So on an average, in 3 months, it used to get filled. So after filling up with the biosolids, we used to leave this geotube as it is for 4 to 6 weeks. So the biosolid, so the self-composting in the biosolid could take place because this biosolids, it has microbes, human fecal matter, obviously it contains microbes. So with the help of that microbes, only this self-composting is used to take place. And rest thing is, which is of major concern, that is pathogens, like how we can remove the pathogens from the biosolid. So what the advantage of this bag
Ma'am,
is like.
sorry to interrupt you, but due to time constraints, I would request you to kindly wrap up soon.
Okay, I'll wrap up. Okay, so the pathogens is also getting killed within this bag only with the help of, this bag, it has heat trapping capacity, and it used to trap sunlight and all with the help of that, and it's closed only, so the temperature used to increase up to 50 to 55 degrees Celsius, which is in most of the cases it's sufficient of killing the pathogens. Next slide, please. So you can see here, this is the image of our geotube bag. This one is like what we have separated our residue from the water, you can see here. And this is the image, the raw sludge. This is after the geofiltrate, the sludge which get passed after the geotube, and this is the final image of the treated water. You can see here, these all are the filled geotube bags. Next. This one is called, this is in-house made, this is called Pluto. This is electromechanical modular system designed by our ourselves only. So it has the system of dosing and tertiary treatment, all the things we used to do in this Pluto also, and its size is very small, so its footprint is also reducing in terms of area. And this is Jocasso. So like primary settling, then for anaerobic treatment, then for aerobic treatment, then for aerobic treatment, and then for the secondary settling. So currently we are not using this system because as we are in the need of getting the BOD less than 250 mg per liter, but currently we are not getting because our septage is not constant, and in most of the cases we are receiving septage with high level of BOD and COD. So it's not working, but still it's we are using this Jocasso system for the septage, or we can say for the sewage water having less than, having less BOD, less than 20,000 mg per liter. Next. So here you can see, this is a slide where we are using our treated water for green belt development, and we have grown some vegetables also with this water, like you can see ridge gourd, green peas, pumpkin, banana. And this is the biosolid which is which got pulverized with the help of pulverizer after 4 to 6 weeks. And we have done all kind of sort of experiments, like to estimate its nitrogen and potash content. So it was worth enough. Next. So you can see these two images are from the epistemic plants from Rajam Sirikakulam, and one is from Amavaripet, Warangal. Like this, we have 6 to 7 more FSTP plants, and a few FSTP plants are coming in coming time. Next. So here you can see this is what the expected increment on an average we have taken, like through the experimental basis, like we used to get COD of around 15,000, in some extreme cases 20,000.
Ma'am, sorry to interrupt you, but due to time constraints, I think we have to finish the presentation now.
Okay. Just move on for the further slides. I'll finish. So I've shown you these slides already. I mean, these images already, biosolids and all those things. It has the pathogen content less than 1, and we have done testing for total coliform. It's we got around less than 100 and 200. Next. So these are the vegetables which we have grown with the help of our effluent and the biosolid we have used as a conditioner. You can see this, the difference between the red soil and biosolid mixture, 1:1 ratio. You can see the growth of the okra in 2 of the cases, how much it's varied. Next. So you can see here there is a bund and we have grown okra here. So you can see clearly the difference between the two. With the biosolid, the size of the okra plant is large, and even your okra pods are also large. Next. So this is the thing what we have gone, result what we have gone after our study. Like this is with the red soil and this is with experimental. There we got a lot of difference between our weight between the 2 okras.
Ma'am, sorry to interrupt you again.
Last, this one last.
Yeah, this is the last. Okay, thank you, ma'am. So Kalyani, over to you.
Thank you, ma'am, for the wonderful presentation. Sorry, due to time constraints, we are already running late by 1 hour, so we had to wrap up. Any questions, Rachna, ma'am?
It was a very, very good presentation. I just want to ask my question. Which polymer you have used for like selection of suspended soil?
Sorry, pardon?
I will repeat the question. So ma'am asked that which polymer have you used for
okay, we have used medium
polymer you have used for the suspended soil.
So we have done extensive study, like we have done hit and trial method. So for Septach, at the end we get to know like medium molecular cationic polymer is working fine with that. So we have used that one only, which is biodegradable in nature. So I can't reveal the name of, because of the trade secret and all those things, but we have used cationic medium molecular biodegradable polymer.
Okay. Thank you, ma'am. If there are any other questions by the participants, I will request you to kindly post them in the chat box and we will send it to ma'am. Thank you, ma'am, again for the wonderful presentation. Moving ahead, next we have a keynote talk by Dr. Parimal Pal from NIT Durgapur, who will be speaking on managing coke over oven wastewater with a circular economy approach. So over to you, Aryan.
Thank you, Kalyani. Dr. Pal, I would request you if you can just unmute yourself and start your video.
Okay.
So we have your presentation. So shall I present it from my end?
No, I'm sharing my screen.
Okay.
Do you see the slides, please? Are the slides visible to you? Hello?
Not yet, sir.
Not yet?
No, sir. So can I do it from my end? I have your presentation.
Actually, I'm reopening it. Let me see.
Okay. Yeah, it's
coming.
Yeah, it's coming, sir.
Okay.
You can put it in full screen, sir.
Okay, I will put it.
Yeah, it's visible, sir. You can start the presentation.
Okay. At the outset, I would like to thank the organizers of the conference for giving me the opportunity to speak at this platform. I have been in Durgapur for the last 30 years, and in Durgapur, there is a steel plant of SAIL, that is Steel Authority of India Limited. And in the Durgapur steel plant, they make metallurgical coke in their coke oven plant for use in the blast furnace during steel making. And that coke oven plant produces hazardous wastewater, and that is treated by their conventional biological treatment plant. So a few years back, this plant authority of Durgapur steel plant approached us in connection with a problem on their BOD plant. So I visited their plant, and I found that it is a basically activated sludge-based biological treatment plant for their coke oven wastewater. And prior to discharging the wastewater to the activated sludge plant, they of course go for neutralization and equalization of the stream. The main problem that they were were actually communicated to me was that the plant was not really working successfully. It was failing to adhere to the norms of the Pollution Control Board. So the Pollution Control Board actually had imposed a heavy fine on them, even warned them to stop the functioning of their coke plant. So they signed an agreement with us and requested us to analyze the causes of the failure and to suggest the remedies. So what I did was that I visited the plant with a team of our researchers, and we found that a huge amount of coke wastewater is coming from their coke plant, and that is used in quenching of the hot coke mass, that is used in washing the ammonia steel, that is used in cooling and washing the coke gases, as well as in the byproduct processing. And on inquiry, I found that around 4,000 meter cube of fresh water is used there for every 1,000 tons of coke production. And in this process, around 1,000 meter cube of hazardous wastewater is being generated. And this wastewater, when it is not effectively treated, is eventually escaping into the river Damodar. And you understand that it is a serious pollution problem of our drinking water source, because we in Durgapur get our drinking water from the river Damodar. So the failure of the biological treatment plant was resulting in actually dysfunctioning of the biological treatment plant. I analyzed the causes there. I took the sample from the BOD reactor itself, and I found that there was not a single living bacteria in that, though it was a biological treatment plant. And I simultaneously collected samples from different points of the plant, and we analyzed those water samples here in the lab, and we found that the wastewater contains quite high levels of cyanide, phenol, ammoniacal nitrogen, thiocyanate, oil, and grease. So all the pollutants are quite toxic in nature. Conventionally, such pollutants can be taken care of by methods like sedimentation flotation, adsorption, steam tripping, wet air oxidation, chemical oxidation, coagulation precipitation, ozonation, electrochemical oxidation. But all these methods, though very successful for taking care of individual contaminants, were alone not effective in taking care of all the contaminants present in such a complex wastewater stream. So we were analyzing, can we think of a new method that can work in such a case? So in our Environmental and Membrane Technology Laboratory of the Department of Chemical Engineering, NIT Durgapur, we started a research with combination of a number of conventional methods like chemical treatment, we coupled with biological treatment, chemical treatment, we coupled with physical separation, chemical treatment, we integrated with membrane separation, biological treatment, we integrated with membrane separation. Then quite a few hybrid technologies were investigated here in our department. And we found that the membrane-based hybrid technology could be quite effective in the tertiary treatment stage. This could help really in reclamation of the water for the purpose of recycling and reusing, and simultaneously, we can also recover some byproducts. While analyzing the causes of the failure of the plant, I found on inquiry of the concerned people that nobody was really taking much interest in successful running of the plant. Biological treatment plant is quite sensitive to the operating parameters like concentration of toxic contaminants, pH, temperature, flow, and all those. I inquired about the people involved there in operating and managing the plant, and I found that hardly anybody had the clear idea of successful functioning of such a plant. And there was practically no monitoring on hourly basis of operation of such a plant. And the major reason behind this that could be traced to was lack of interest in the people in running such a plant. Actually, wastewater treatment plant in an industry like the Durgapur steel plant draws very little attention of the management, draws very little attention of the policymakers, engineers, and operators, because operationally it is quite boring and it does not produce any revenue. Only out of compulsion, such a plant is operated, and where the level of ethics is low, where the compliance of regulations is low, where the punishment on violation of regulation is low, nobody will really take interest in successful running of such a plant. So the idea came to my mind that can we not think of running such a plant in a different way so that it becomes operationally attractive, technologically interesting, and at the same time economically viable and gives some revenue, so that it becomes attractive to everybody, to the operators, to the engineers, to the policymakers, to the management authority. And we carried out quite a number of investigations here in our lab, and we found that the wastewater from the coke oven plant is quite rich in ammoniacal nitrogen, and that could be successfully recovered in the form of a byproduct called struvite. Struvite is actually a salt, a slow-releasing fertilizer that combines phosphorus, magnesium, and this nitrogen. This ammoniacal nitrogen from the wastewater source can be recovered there as struvite on addition of some phosphate and magnesium salts. So we started investigation, and we found that in the conventional wastewater treatment plant, where long time is being required, where huge cost is being involved, high power consumption is being involved, and despite all those, the plant is meeting frequent failures. So such a membrane-based, if we can think of a membrane-based hybrid technology that can effectively treat water for its reclamation, for its reuse through recycling, as well as recovery of a useful value-added byproduct like struvite. So we carried out investigation, and we found that first the chemical analysis, through chemical analysis, we find that if we use some magnesium and phosphorus salts here, then ammoniacal nitrogen can be precipitated out as struvite, as TrueWhite, but there may be several combinations of such magnesium and phosphate salts. So therefore, we have to find out the best option. For example, there may be a combination one where we use magnesium chloride and sodium phosphate. The second option is magnesium oxide phosphoric acid, and there was a third option of calcium phosphate and magnesium sulfate. With all these three, we started investigation on the TrueWhite precipitation aspect, and we found that the salt combination, for example, magnesium oxide phosphoric acid, if we add, then the precipitation of TrueWhite is quite low, because and that really results in low MAP precipitation and low ammoniacal nitrogen removal. And we also tested that, yes, the ratio, appropriate molar ratio of magnesium, ammonia, and phosphate is also very important in this case. And in one such a study, we found that, yes, at a ratio of 3:1:1, we find that this reduction in COD, that is the overall reduction of the pollutants, is quite high. Then we also tested the ratios of magnesium and ammonia, phosphate and ammonia, and pH ranges in the different ranges, like 0.75 to 2.5 for magnesium ammonium, 0.5 to 1.5 for phosphate ammonia, and pH range 7 to 10. And we optimized the process conditions using the response surface optimization technique. And we found that eventually, if we go for magnesium ammonium ratio of 1.6, phosphate ammonia ratio of 1.0, and we conduct it at a pH of 9.1, then we can achieve more than 95% removal of ammoniacal nitrogen. And we also investigated how the crystals are being formed, whether they are really, conforming to the theoretical structures. So we had gone for dispersive X-ray analysis, and we had gone for gravimetric analysis, XRD analysis, and through all those, we just found out, yes, the crystals, the TrueWhite crystals that we are getting were really actually conforming to the theoretical structure of the compound. And when we were successful in this initial investigation, we eventually developed a membrane-integrated hybrid system. A small scheme of that is presented over here. Actually, we had investigated with several combinations. We have developed here in our lab almost a pilot scale unit, and a part of that has been shown here. And this scheme shows that we basically use a CSTR, that is continuously stacked tank reactor, where the influent wastewater is charged, and magnesium and phosphate in the doses as decided through our optimization study are added here, where this addition in this reactor eventually leading to production of TrueWhite, and the major part of this TrueWhite settles at the reactor itself, and which could not be settled, that is actually separated out from the medium using a simple microfiltration membrane. And then after the recovery of TrueWhite, our purpose of this new scheme was to reclaim the water so that the water could be reused. Therefore, we had gone for subsequent downstream purification of this water stream, and where we have actually engaged a flat sheet cross flow nanofiltration membranes. And we in those days actually imported some commercial membranes from Septo membrane international manufacturer from America. And these membranes we had in different varieties, like we had nanofiltration membrane 1, 2, 3, and then NF20, NF200. Several such NF membranes we investigated here. And from these investigations, we found the best membrane for best suited for the purpose. And one major problem that is often encountered in membrane-based separation process is the fouling of the membrane. And conventional membrane modules which have so far been used are dominated by actually hollow fiber types or spiral winding type. So these types are quite fouling prone, and we found that if we really think of a plant using this kind of modules, then fouling will be very frequent, and it will be very difficult to run such a plant on sustainable basis. So we actually fabricated here a new type of membrane modules which is called flat sheet cross flow membrane module. And the modules actually they had a different hydrodynamics where the fouling of the membrane is largely overcome. There is a sweeping flow of the fluids over the surface of the membranes, and this sweeping flow of the fluid prevents accumulation of the suspended solids on the surface of the medium, and thereby permitting long time operation of the membrane without frequent cleaning and without replacement of the membrane. So we were really successful with our selected membrane and with our
Sir, sorry to interrupt you, sir, but due to time constraints, I would request you to kindly wrap up.
Okay, I will just wrap up.
Yes.
So we were really successful in developing the system. This membrane integrated hybrid system, that scheme that you see, this was eventually proved to be very successful, and we could run it for long hours without encountering the problem of membrane fouling. And finally, we found that yes, through this integration of membrane-based separation with a conventional chemical precipitation, we not only take care of the hazardous chemical contaminants of coke wastewater, we reclaim that water that can be reused within the plant itself, and through the production and marketing of the stupid fertilizer, we can make the plant economically quite attractive. And we therefore concluded that such a membrane-based hybrid technology would really be a sustainable technology to be used in such complex wastewater treatment scheme. Thank you all. Thank you. If you have any question, you may ask.
I'd request our participants, like if they have any questions, then they can raise their hands. I'd request our chairperson, like, ma'am, if you have any questions for Dr. Parimal. Okay, sir, I think if there are no further questions, then we can wrap the presentation. Thank you so much, sir, for the presentation.
Welcome.
Just a minute, Arun. Actually,
okay.
Ma'am asked that in one go.
Yes.
In one run, what is the total volume of wastewater that can be treated?
Yeah. Would you please repeat? Yes.
In one run, what is
bio?
the total volume of wastewater that can be treated?
In bioreactor.
So she's asking that in one round,
in one
what
run,
volume of wastewater will be treated?
Volume of wastewater that can be treated?
No, actually, you see, the industrial wastewater treatment plant, the BOD reactors that Durgapur Steel Plant Authority they have, they are quite big bioreactors, like 4,000, 5,000 liters. That these are the volumes of these bioreactors. They're quite big, and they have it in activated sludge plant form. And actually, they have the problem. That's why we have gone for alternative methods here. So we are not using the biological method here. We have gone for chemical precipitation coupled with membrane filtration.
Okay, sir. Thank you for the wonderful presentation. Now, moving ahead, we'll have the next speaker. Over to you, Aryan.
Yeah, thank you, Kalyani. Next, I would like to invite Atun Roy Chaudhary, sir.
Aryan?
He's from. Hello.
Yes, you're audible.
Yeah. Next, I would like to invite Atun Roy Chaudhary sir from Banka Balu. Sir is specifically working on biomedical waste treatment scenario, and he will be delivering a talk about that and the recent developments that have been done in biomedical waste management. Over to you, sir.
Yeah, good afternoon, everybody. Thank you so much for extending this opportunity, first of all, both to NESA as well as Kalinga Institute of Technology. So could you please give me the right to share my screen? Yeah, I got it. Give me a moment, please. Please give me a moment. Sorry for the inconvenience. I'm sharing my screen.
No problem, sir. So we have your presentation too.
Yeah.
Okay, the screen is visible.
Yeah. I'll just make it full screen.
Yeah, it's visible, sir.
Yeah, fine. So as you have described that today I'm going to talk about the COVID-related biomedical waste management.
Sir, can you put it in a full screen mode?
That's what I'm trying to do. Is it working? Is it full screen now?
Yeah, it's now. You can start.
Yeah, fine. So as you have described, today I'm going to talk about COVID-related biomedical waste management, as well as the regular BMW management and how exactly they're different and how to treat them separately. So first of all, let's try and understand what exactly is biomedical waste. So the waste that is generated during the diagnosis of human being or any animal or immunization process or treatment or any therapeutical process put together, all this waste clubbed together, we are calling it biomedical waste. So it can be of different categories, right? And based on the category, color-coded segregation has been actually recommended for biomedical waste. So color-coded segregation, there are primarily 4 colors that we segregate biomedical waste into. First is yellow color, which includes all sort of anatomical waste, human body fluid, serums, and all other things whatsoever you can think of in terms of anatomy. The second one is red or blue color, where all other kind of sharps and everything needs to be disposed of, including surgical blades and all those things. And then the last one is, IV bottles, glucose bottles, and all those things. And the last color is white, where actually all the sharp like blades and syringes, those need to be disposed of. And the last segregation is based on for black color, which is for the regular municipal solid waste that is generated from the healthcare facilities. What are the impacts of COVID biomedical waste? Of course, there's an environmental impact, human health related impact, and occupational safety related impact due to the secondary infection from it. So these are the previous scenarios of biomedical waste management and handling, which are really devastated to see and witness. So now, post-COVID, definitely the scenario has been improved a lot. I do have a lot of slides, so I don't have much time to explain each of them, as because time is pretty stipulated here. Already I have talked about this color-coded segregation for different categories of biomedical waste from category 1 to category 10. Of course, this white color one, it needs to be, as because it is puncturing material, puncture causing materials, that's why it needs to be contained in a hard container, whereas yellow and red or blue, those bags can be non-chlorinated plastic bags. So now due to COVID, previously only one bag was enough for covering this biomedical waste. For covering up or for the disposal, packing up of this biomedical waste, both in yellow and red category. But now post-COVID era, what the Central Pollution Control Board has suggested, rather than going for a single packaging, we should go for a double packaging in COVID biomedical waste management guideline, and that needs to be disinfected within the healthcare facility premises using sodium hypochlorite solution, 4%. So these are the biohazard symbol. Basically, once the operator, they start collecting the biomedical waste, they have to put the symbols on it, whether it's yellow color category or whether it's blue or red color category. Based on that, they need to stick the sticker on to the top of the bag. And these are the always biomedical waste should be conveyed in completely safe mode, where there should not be any chances of secondary transmission, and it should be a covered transmission. So these are the real-time vehicles from Ramki Enviro Engineers Limited, as you're seeing. So this is the biomedical waste collection from Apollo Hospital. And that is how it should be, or it's supposed to be conveyed. So once the bag is completely filled, that's supposed to be separately stacked, and those bags supposed to be filled into this puncture resistant container, white color, yellow color, and blue color, and then they're supposed to be sent to the CBMWTF, that is nothing but the common biomedical waste treatment facilities. So this is what the basic process flow diagram of the common biomedical waste management facility. So once the waste comes in, now the implementation of the barcoding system has been a mandate from Central Pollution Control Board since 2018. Once this new biomedical waste management rule came into the action, and barcoding system is enabled in order to completely ensure that zero biomedical waste illegal disposal. That means whatsoever the waste that is generated, that is going to the CBMWTF, and the entire waste is scientifically handled and treated. And for that purpose, recently in the month of April 2020, I mean, immediately after introduction of COVID, CPCB has come up with a new app called COVID-19 BMW. That means there are 3 different registration categories in that app. First is for the healthcare facilities, second is for the waste collector, and the third one is for the COVID waste management facilities, I mean the CBMWTFs. So what happened, they need to register under their own categories, and each individual of these entities, either it could be healthcare facility, it could be the waste collector, it could be the CBMWTF, individually they need to feed their data on regular basis, and through this common window, the entire data would be actually logged into the Central Pollution Control Board's national system on pan-India basis. So basically what happens once the waste comes in case of general biomedical waste, yellow color waste or yellow color bagged waste supposed to be sent to the incinerators. So in incineration, there are 2 chambers, primary chamber and secondary chamber. In primary chamber, the temperature is about 800 degrees Celsius. In secondary chamber, the temperature is somewhere around 1100 degrees Celsius, and this ensures complete combustion of the waste. And once the waste is combusted, the ash that is generated, the fly ash that is generated, the bottom ash that is generated, that's supposed to be sent to secured landfill after sealing them into cement containers. Whereas the flue gas, the combustion gas that is coming out, recent days, now we are talking about, you know, enabling the waste to energy system out of it, but still the same is yet to be commissioned in India. The flue gas is further purified using scrubbing system, wet scrubbing, then baghouse filter, and then once it is free of all the corrosive gases, dioxin, furan, particulate matter, then it is sent to the stack or chimney, where the minimum height of the chimney should be 30 meters, and then it is the plume is actually dispersed up into the open atmosphere, higher atmosphere. And the waste, other than the yellow bags, the blue color, red color bag waste, they're supposed to be sent to the autoclaving for disinfection, or there are certain other technologies like hydrolysis technology or microwaving technology. Those are also useful for disinfection, but mostly autoclaving is the standard practice, which is in implementation in India in majority of the CBMWTF facilities. Other than that, plasma pyrolysis technology, needle blaster, there are so many other technologies which are coming in, but still they are yet to gain their popularity on the mass market. So once the waste is disinfected in autoclave, which happens at 15 psi pressure over 121 degrees Celsius temperature for 1.5 hours. Once it is completely disinfected, what we actually do, we actually segregate them based on the stream, whether it is glass or plastic, and then they are sent to the authorized recycler for recycling. In between, we are actually conducting spore tests in order to ensure that the waste is completely disinfected and there is no trace of any sort of pathogenicity on it. Moving forward, these are the real-time pictures of the incinerator as you're seeing, and filling up of the ash into the landfill. I have already explained this entire thing. So this is the primary chamber of incinerator. The other one is the secondary chamber. Then the air pollution control devices are commissioned. And then finally, the treated gas is disposed through the plume. So this is again the real-time picture of the incinerator. So this is how a common biomedical waste treatment facility typically looks like. This is the overall footprint. This is the admin building. Then you're having the incineration storeroom, sterilization room for autoclaves, incineration shed, ETP. ETP is one of the major component because autoclave or any disinfection process generates a lot of wastewater. So that needs to be properly treated and reused back, because these systems, they are designed to be zero liquid discharge systems. So you cannot let go a single drop out of the premises, out of the plant premises. So you have to treat it and reuse it back. So where exactly to reuse back? So you can actually reuse it back in your waste scrubbing system. in your wet scrubbing system for air pollution control in the air pollution control device. So that wastewater is once again sent to the ETPs, and there also it's again retreated. So the process flow diagram of the ETP I'll try to showcase. This is, by the way, the autoclave photograph as you're seeing here. So this is the typical process flow diagram for an ETP that is operating in CBMWTF. So flocculation tank, then sedimentation where the suspended solids and colloidal solids are mostly removed. And then after that, it goes to secondary settling. From there, it again goes to settling through tube settler. And then finally, it is disinfected. And then it's finally filtered using sand filter, activated carbon filter, micron filter. And the sludge that is generated is sent to sludge drying bed for drying and further moisture removal. And the sludge is further packed into cement containers and sent to secured landfill for landfilling purpose or for deep burial in case of absence of landfilling within 75 kilometers of radius. And the final treated water can be used in cooling tower and scrubbing system. So this is what the typical process flow diagram. This is the Venturi scrubbing system for the air pollution control device. This is the effluent treatment plant photograph. This is how the actually in the cement containers, the sludge and the ash, they're getting filled off and they're getting disposed into the landfill. The landfill photograph is also shown. This is the footprint of a common biomedical waste treatment facility. This is the incineration plant you're seeing here. This is the overall footprint. This is the team, Ramki team, my former organization where I've been working for last 5 years. And this is once again the plume. You can see the plume is getting dispersed from the stack or chimney. So this white plume, it signifies the operation is actually compliant. There are certain standard or norm that actually gets monitored through a common emission monitoring system, CEMS, and the data is logged into Central Pollution Control Board's data logger system, where particulate matter, SOx, NOx, particulate matter 2.5 and 10, these are all the things actually we monitor. The limits are there, like 80 microgram per meter cube, 60 microgram per meter cube, 100 microgram per meter cube. These are a couple of real-time photographs of the CBMWTF plants. And for COVID waste here, I would like to do one more value addition. For COVID waste exclusively, Central Pollution Control Board has recommended that entire COVID waste is supposed to be incinerated without any other treatment, and there should not be any manual contact involved into it. So for that, mechanical feeding system has been developed, and entire chunk of COVID waste is packed into 2 different layer of packaging, and then it is disinfected within the HCF's premises using sodium hypochlorite of 4%, and then it is sent to the common biomedical waste treatment facility where it is incinerated off, and then finally the ash is disposed into secured landfill. Here in this regard, I'd like to include one more thing. Previously, during the first wave of Corona, there was a huge amount of COVID-related BMW generation because people, they were actually skeptical about even the regular MSW that is generated from the HCFs. They were afraid of touching it. But later on, due to proper training, due to proper awareness camps, the conduction of awareness camps, and the training of the people working in this domain in healthcare facilities, better segregation took place. So though the number of active cases during the second wave has been multiplied, the maximum number of active cases has been multiplied by 4 times when compared to the first wave, the waste generation has not been parallelly incremented because of the better segregation. So MSW actually has been segregated in a proper fashion. Food waste has been properly segregated in a proper fashion in HCF, and that led to the reduction of burden into healthcare facilities. So we believe the similar kind of awareness would be constantly growing among the healthcare professionals as well as the waste management professional, and that will lead to minimization of COVID-related biomedical waste generation, and that would enable or help the CBMWTFs to better execute or better handle and manage the COVID-related waste, because already, if you go by the numbers, 80% of the common biomedical waste management facility, approximately in our country at today's date, we have 203. We have 203 common biomedical waste treatment facility, and those are majorly located in states like West Bengal, Andhra Pradesh, Tamil Nadu, Telangana, Delhi, and all those. So if we talk exclusively Northeast state, they are having any common biomedical waste treatment facility. So we need to have more number of common biomedical waste treatment facilities in that should be the first agenda in order to cope up or tackle with the huge or gigantic volume of biomedical waste. And the second thing is, rather than going for decentralization where the topography is not very favorable, we have to go for individual waste treatment facilities with GHCFs, where individual incinerators can be commissioned along with the deep burial facilities for the ashes to be disposed of.
Sir, sorry to interrupt you, but due to time constraints.
Yeah, I'm done. I'm done. So thank you so much for your patience listening. If you do have any question, please feel free to ask. If anyone has any question, please.
Any questions? Okay. Thank you, sir, for the wonderful presentation. Next, going forward, we will, unfortunately, Dr. Saxena won't be able to join us for today's talk. So we will be moving ahead with the talk by Arnab Pal from Wattman Saitiva. Will be speaking on Wattman capabilities for environment monitoring. Over to you, Arnab.
Yeah, thank you. So I'm sharing my screen. Can you allow me to share?
Could you please unmute?
Am I audible? Hello, am I audible?
Yes, sir, you're
Yes, sir.
audible.
You're audible, sir.
You're audible, sir.
Yeah, I am not able to share my screen. Will you allow
Sir,
me?
you are still not audible.
Kalyani, we can hear him.
Please allow me to share the screen.
Yes, sir. Yes.
I am not able to share my screen. Otherwise, you can share my.
Sir, I have your presentation. Can I share
Yeah.
it from my end?
Yes, yes.
Okay. So the screen is visible?
Notes. Yeah.
So you can start the presentation.
Okay, okay. You can go to the next slide, please. So I am Arnav Paul from Saitiva, Wattman. We do have the air, water, and soil monitoring products. So I will just brief it about. Go to the next slide. Yeah, for the air, we have the air monitoring products like the glass microfibers, thimbles, EPM 2000. Since the air monitoring norms were established, Wattman products have been recommended and used for air particulate sampling and analysis. This includes the gravimetric analysis for the airborne particles, both the PM10 and PM2.5, and the total suspended particulates stack monitoring. For those processes, the Wattman is used. So air pollution monitoring, especially the stack and aerosols, require a filter that can withstand chemically harsh environment and high temperatures. High purity quartz is also favored for this reason, along with the applicability of the metal analysis. So both for the PM10 and PM2.5, for the air monitoring, Wattman do have the glass microfibers, the membranes, PM2.5 membranes, and for the higher temperatures, the quartz microfibers. Please go to the next slide. So these are the parameters for the filters offered by the Wattman for the gravimetric analysis and chemical determinations. The GFA sheet, which is used for the ambient air monitoring, this can withstand 550 degrees centigrade, has the thickness of 260 micron. The particle retention is almost 99.9%. EPM 2000 is used for the trace metal analysis like the lead, antimony, bismuth. The temperature resistant here is also the 550 degrees centigrade, and it is thickened to a 450, almost double of that of the glass microfiber, and each is sequenced, means each filter paper is been numbered, so it can be used for the research paper also. And beside that, we for the higher temperatures, we have the quartz microfibers at the different grade A, B, C, and high performance grade, which can resist the temperature of 800 to 1200 degrees centigrade, having the particle retention of 99.9%. And we do for the higher temperatures also, and if there are the chemicals involved, so we do have the the above are the binder free, and for any chemically inert, we do have the filters with the binders. So next one. Yeah, for we Wattman do have the continuous air monitoring tapes. Wattman glass fiber tapes for continuous air monitoring are compatible with air samplers from multiple manufacturers globally. GF10 is a standard filter for the beta attenuation method. HGF61 is further developed for the high humidity environments. These are the, on the right hand side, you will find the reels of the different size, 30 mm by 20 mm, 70 of the different size and dimensions is available to fit any global manufacturer continuous air monitoring products. Next one, please. Yeah, coming to from the 10 air monitoring particulate matter 10 now to the PM 2.5. These are made of the membranes surrounded by a polypropylene ring. Wattman PM 2.5 PTFE filters are used for the measurement of fine particulate matter in the atmosphere for the PM 2.5. You can refer the right hand side chart also with the ASTM's data, and it is 47 mm Teflon, pure Teflon filters. Next one, please. Yeah, grade 72 is used for the radioactivity of air particulate sampling. Grade 72 is a composite cellulose and glass microfiber filter loaded with the activated carbon. It is recommended to be used for the absorbed radioactive iodine in air pollution monitoring and in the nuclear installations. You can find different diameters according to your suitability. Next one. So for the asbestos, nanoparticles, and the microplastics, asbestos analysis, you know, asbestos is banned industry. For the asbestos analysis is commonly undertaken by a number of microscopy techniques like the scanning electron microscope and transmission electron microscope and phase contrast microscope also. We do have the polycarbonate, which are the trackage membranes starting from the nanopores of the 15 nanopore membranes, mixed ester membranes, and anopore, which is the only aluminum oxide membrane, which is the inorganic membrane ranges from the Wattman. Next one. Yeah, for the water monitoring, we do have the total solid analysis workflow using the filtration based method. So you can prepare your filter according to the washing and weighing, then drying the sample, then calculate the weight, then heat retain and evaporate the liquid filtrate and weigh the retained solute to calculate the dissolved solids. So these are the gravimetric analysis of the weight of the water monitoring process. Next one. So these filters of the glass microfibers, see especially the GFC and 934 AH is used specially for the total suspended solids, total dissolved solids, and total volatile solids in water. There are also another products of 934 AH ready to use. We call it RTU, where the casket is already been given. The casket is pre-weighed and numbered also, so you have not to weigh. You can avoid many steps of washing and drying methods. Next one. So beside this, for the gravimetric analysis, we do have the products. For the microbiological analysis, we have the manifold system to hold the membranes, to hold the different set of membranes. So this is the manifold. It can be automated also. If you have the large quantity of samples with a paddler, it can be automated. So next one, please. Yes, so we do have the membrane filters. We provide a wide and versatile range of membranes. So these membranes are appropriate for depend on the methodology being followed in your laboratory, especially if the mixed tester and the microplast membranes are sterile and individually numbered also and individually packed also. So we do have the nylon, polyamide membrane, cellulose mixed testers. So this can be wide, gridded, colored also for the colony counting purposes. So you can use for the different study of the bacteria. Next one. Yeah, coming to the soil. For the soil analysis, for measuring the soil nitrogen content can help refining the nitrogen fertilizer addition. So nitrogen content analysis is typically done when the Geldal technique, which involves sampling of an exact amount of soil before transfer to the digestion tube. Low nitrogen content weighing paper makes the sample transfer easy and quick without loss of materials and with minimal interference with the end itself. So the sample may need to be filtered with a Wattman branded qualitative filter paper prior to analysis. Next one. Yeah, so for the spectroscopy and chromatography, trace element analysis in soil generally involves determination of essential nutrients for plant growth, example potassium, magnesium and calcium, and detection of the potential heavy metal contamination of the lead, chromium, arsenic, zinc, copper, cadmium and mercury, and also for the colorimetric for the phosphorus analysis. To determine the soil phosphorus content, the soil is extracted with a chemical solution and the phosphorus content in the exact is measured by the colorimetry. So filtration of the extract through a qualitative filter paper is recommended and generally needed before analysis. If an automated method is used for determining phosphorus concentration, acid resistance filter paper may be needed. That is the 541 graded. So thank you.
Thank you so much, sir, for this presentation. I would request our chairperson, if there are any comments, then you can ask.
Ma'am, you can please say the question. I'll repeat it from the question.
Hello. Just I wanted to know the cost of filter paper 2.5. What is its actual cost? And what is the market cost? What cost they in its fabrication? How much cost is involved, and when it stays in the market, how much they pay? What is profit in between?
Sir, am I audible?
Water filter paper are really very costly. So in one use only one filter paper can be. In one only one filter paper can be.
Sir, am I audible?
Yes, Kalyani. Yeah, you are audible.
Yes, the question is that Wattman filter paper, they are really very expensive. So what efforts are being taken by Wattman to reduce the cost?
Oh, thank you, ma'am. Thank you for the generosity and for your interest, inclination towards the Wattman. Definitely, we are working and we like to work with the researchers. As you know, that am I audible?
Yes, sir, you're audible.
So we are working with all the pollution control boards and the CPCB. Definitely, if you come with the inquiry, we will try to address it directly towards your institute or any researchers, those who are in the research institutions. We will not go through our channels. We will try to support you directly, and hopefully that will be the cost concerned to you.
Okay. Thank you, sir. Thank you, sir, for the wonderful presentation and for being with us here today. I would like to thank all the speakers of this session for their comments and their sharing their views on today with us and all of the audience who are there online. Next, I would like to call Professor Javed Ahmed to come on stage to felicitate the chairperson for the session. Thank you, ma'am. Thank you, ma'am, for coming here and being chairing this session. We are at the end of our fourth technical session. We'll break for lunch right now, and then we will join for the fifth technical session at 2:30 p.m. sharp. Thank you.
Hello, everyone. Welcome back after the lunch. Next, we are proceeding with the fifth technical session of the day. I would like to invite Dr. Amrita Mishra as the chairperson of the session. Just to brief you about ma'am's profile, Dr. Amrita has completed her PhD in 2002 in Food Science and Technology from Chonbuk National University, South Korea. She is associated with School of Biotechnology, KIIT, as an assistant professor. Her research interests include characterization of biomolecules for potential antibacterial application. She has received several accolades for her contribution in the related fields that includes TBT Biocare Scientist, Government of India, Young Scientist Research Grant from BST, Government of India, etc. Her current focus is in the development of biogenic nanostructures processing for applications in wound management. With this, I take the privilege to welcome you, ma'am, on the dais. Over to you, ma'am.
Thank you, Aryan. Good afternoon to one and all present over here, as well as the online participants. I welcome you all to the post-lunch technical session of the conference. I would like to introduce our speaker for this session, Professor Cecilia Stalsby-Lindberg. So Professor Cecilia is a professor and group leader for the Research Group Health System and Policy at the Department of Global Public Health, Karolinska Institute, Sweden. Her research concerns antibiotic resistance with a focus on improving infection, prevention, and the use of antibiotics, as well as a reduction of spread of antibiotics and antibiotic-resistant bacteria in the environment. She has supervised many master students, doctoral students, and postdoctoral fellows within the research field. Additionally, she is academic coordinator at Karolinska Institute for collaboration with India and has collaborated with researchers in India for almost 20 years. I welcome you, Professor, on behalf of the organizing committee of the conference and request you to begin with the talk. Over to you, Professor.
Yes, good afternoon, Amrita, and all of you in the conference. Many thanks for inviting me. I hope, can we see, now I'm trying to share my video, or sorry, my screen. Can I do that? It says I can't do that.
Ma'am, you have the access.
Sorry?
You have the permission to share.
Yeah, now it seems to work. Can we see? And then I would like to have the full screen also. Yeah, but now we are in the wrong place of the presentation, so we have to go back. Sorry for this. I don't know why it happened like that. So many thanks for inviting me. This is maybe a slightly different kind of presentation that I hope that will contribute to the overall aim of the conference. And as Dr. Amrita said, I have the privilege to collaborate also with KIIT since many years, both with Dr. Amrita and with Dr. Sorry? I can't hear what you're saying. Sorry?
Ma'am, can you put the presentation?
Yeah, I have my presentation here. It says that I'm screen sharing, but I can stop sharing and start sharing again. Can you see something now? Can you see the presentation now?
Yes, sir.
Now you can see it.
Yeah, ma'am, you can continue.
Yes, thank you. So I was just saying that I have the privilege of collaborating with Dr. Amrita Mishra and Dr. Suraj Tripathi since many years. And I'm contributing sort of the public health part. Now I will give a slightly different presentation maybe to this conference called Antibiotic Resistance, a Global Perspective. So now this doesn't want to work again. I want to, I don't know why I can't change the slide. I want to, oh, this is, I have to stop sharing again and I have to start sharing again. This is.
Ma'am, we will share it from our end.
Sorry?
We will share our presentation from our end, ma'am.
Yeah, but then take the final one, which I sent just 15 minutes back. Yeah, I don't know why this doesn't want to. Did you receive the presentation just 15 minutes back? Hello?
Ma'am, we can see the presentation.
Yes. So this is not in presentation mode, but maybe that is okay anyway. Is this? Yeah. So anyway, I will show it like this as it doesn't work. So why is then antibiotic resistance a global concern and why is antibiotic use important? As you all know, there are a lot of resistance mechanisms developing and spreading globally, and this has a lot of implications for treatment of infectious diseases and also for a lot of other procedures and treatments in healthcare. So the Director General Margaret Chan, or the former Director General Margaret Chan in 2012 said, a post-antibiotic era means in effect an end to modern medicine as we know it. And as you all know, bacteria are different and they have a genetic mechanism that can spread resistance. It can be spontaneous mutations, it can be transfer of resistance genes. And then this is complicated by the use of antibiotics, both the human and the non-human use that selects for resistance. And this is further complicated by crowding, travel, poor hygiene, poor infection control, and the environmental spread. And this leads to spread of antibiotic-resistant bacteria, antibiotic residues, and antibiotic resistance genes, both in the hospitals, in the community, and in the environment. And presently, there is a lack of point-of-care diagnostics. There is a lack of new treatments that will not create resistance. And there is also a lack of ways to reduce the environmental spread. So these are all areas that we are working on. If we see it from the environmental perspective, both human use, non-human use, and the pharmaceutical industries, they spread antibiotic residues in the environment, and they also spread, of course, resistant bacteria and resistance genes. And this comes then back to the humans and to the animals through food and through drinking water. We published a paper some years back now on the antibiotic residues in the environment of Southeast Asia. And we calculated that there are many, many tons of active antibiotic residues or active metabolites that goes out in the environment. We have also done studies in China, for example, where we have seen the presence of antibiotic residues in various environmental compartments, including then also vegetables and drinking water. So then we want to do something to work for solutions, and that is where the collaboration between KIIT and KI comes in. So both with Dr. Amrita Mishra here and with Dr. Suraj Tripathi and with many of their postdocs, PhD students and master students, we have been working with various solutions, either to find new ways for treatment or to find new ways for removing or neutralizing antibiotic resistance and bacteria in the environment, especially water solutions. I will come back now to antibiotic use. And what you can see in this slide is the more or less straight relationship between antibiotic use on the x-axis here and the proportion of resistance. This is just one example on the y-axis. And the ECDC, the European Center for Disease Prevention and Control, said just now in 2021 that in the community that is outside of hospitals, the emergence and spread of antibiotic-resistant bacteria is mainly driven by the inappropriate use of antibiotics. Because we also need to realize that antibiotics are life-saving medicines, so they should be used in many circumstances, but we need to reduce this inappropriate, or what we can call the irresponsible use of antibiotics. It has been estimated some years back that today about 700,000 persons per year die from antibiotic resistance or antimicrobial resistant infections. And if we cannot do anything to mitigate this problem, this will increase to maybe about 10 million in 2050. So something needs to be done. And WHO has, of course, worked with this for many years. Already in 2001, the WHO Global Strategy for Containment of Antimicrobial Resistance came. It was for many reasons not implemented, mainly because of lack of funding and so forth. In 2015, the Global Action Plan came, which also requested member states to develop their own national action plans based on their specific contextual characteristics, and that many countries have done. I will show that later, including India, of course. And in India, there has also been some state action plans. The first one was Kerala, and then Madhya Pradesh, Delhi, and I'm also aware that Odisha is working with the state action plan. I'm not sure exactly how far it has come. In 2016, the United Nations General Assembly also pointed out that the issue or the challenge of resistance as a very large, big issue, also from the economic perspective. The Global Action Plan has 5 objectives: strengthen knowledge and evidence, optimize use of antibiotics, reduce the incidence of infection, awareness and understanding both among the general public and among healthcare providers and policymakers also, and then also new medicines, diagnostic tools, and vaccines. I'm sure that you are all aware of the UN Sustainable Development Goals. We have gone through all these goals, and we have realized that these goals will not be possible to attain unless much more focus is put on the containment of antibiotic resistance. So this has implications for many parts of the development goals. Just very recently, December 1st, 2021, the so-called joint tripartite, the FAO, the Food and Agriculture Organization, the OIE, the Animal Organization, and the WHO, and also UNEP, the United Nations Environmental Program, together made a statement on One Health. And One Health, that is, the combination or the importance of looking at humans, animals, and the environment together. So they now say that One Health is an integrated, unifying approach that aims to sustainably balance and optimize the health of people, animals, and ecosystems. It recognizes that the health of humans, domestic and wild animals, plants, and the wider environment, including ecosystems, are closely linked and interdependent. The approach mobilizes multiple sectors, very important, multiple disciplines, and communities at varying levels of society to work together to foster well-being and tackle threats to health and ecosystems, while addressing the collective need for clean water, energy and air, safe and nutritious food, taking action on climate change, and contributing to sustainable development. So this is a very new definition now. And they have also put it in this figure where they point at the communication between the different sectors and society can lead to increased health at all aspects, the so-called One Health. We also looked at the One Health perspective in Sweden's policies for containing antibiotic resistance. Sweden has a very long-term work against antibiotic resistance. And we saw that already in documents from 1959, the One Health perspective was taken up. If we look at antibiotics use worldwide, on the upper figure here, we see the sort of pressure of antibiotic use. The darker, the more antibiotic use. And the lower figure shows the increase or decrease in antibiotic use. Red, increase, blue, decrease. And as you can see, India has a quite high increase in antibiotic use. But we should also remember that the baseline level in India was not very high. So in many parts or pockets, antibiotic use is actually too low. And that is important, that we need to look at the different contexts when we talk about antibiotic use. And we can never say stop using antibiotics because antibiotics are life-saving, as I just mentioned. If we come to the European Union or the European part of the world, we can see a very wide variation here in antibiotic use. And if we look at compare with India, India would be here somewhere in the middle of the European Union use. We can see here Greece, for example, have very high use. We can also see that Belgium is here somewhere, has a high use, while Netherlands, which is a neighboring country to Belgium, has a very low use. And therefore, we don't think that these are differences in disease patterns or anything else. So we more think it's the differences in health systems or differences in insurance policies or other things that are related to the health system. If we look at the seasonal variation also, we see that those countries with high use, they have a huge seasonal variation, while Netherlands, again, has a very low seasonal variation. Again, we think this has relationship to guidelines and other things. So this the wide variation here, we assume it belongs to use of antibiotics for viral infections, where it of course doesn't have any effect at all. We come to Sweden then, country I come from. We see that dispensed antibiotics per 1,000 inhabitants per year for different age groups here from 87 till 2020. These are children. They had high use here, almost 1,400 prescriptions per 1,000 children per year in around 90s. Now we are down here in 300 prescription per 1,000 children per year, meaning that one child in every third gets an antibiotic prescription now. And now we have the elderly age group above 65 having the highest antibiotic use. We can also see here a sharp decrease in 2020 during the COVID pandemic, which is maybe surprising to some, but this is the situation in Sweden. We have been working with something called STRAMA, the Swedish Strategic Program Against Antibiotic Resistance, since 1995. I was involved in the national group here for almost 15 years. And we believe that the key to implementation is the national coordination and local commitment together. Sweden is, of course, a very small country. We have only 10 million inhabitants, but it's still quite geographically spread. And it's very important this with the local groups. STRAMA has been seen as a kind of role model for many countries to implement this kind of multi-sectoral, multi-professional groups in regional places. And we had a collaboration also with the Indian NCDC some time back now. And there in that project, we described the situation in Sweden. It's a quite interesting book this, that is available online. We have also described the Swedish work, and the Swedish situation is available online also, if someone is interested. I will then come to the European Antibiotic Awareness Day. Since 2008, we have had one day, and me and my research group, we have been involved in many different aspects of this. This little hedgehog has been the sort of symbol for this. And it then increased to the World Antibiotic Awareness Week and World Antimicrobial Awareness Week now. And the latest week was in November 2021. The theme here is spread awareness, stop resistance, meaning that everyone needs to be aware of the situation and need to do whatever they can to stop the resistance development and spread. We have also been working with Vietnam, and if you remember, in Sweden, 1 in 3 children below 5 gets an antibiotic prescription every year. In this situation here, almost half of the children got antibiotics in 4 weeks. So then we realized that there is a need to have some kind of intervention here. We had that together with the Hanoi Medical University. We tested this hedgehog, which we think is a sort of nice symbol with the message is then if you have a cold with cough and fever, but no difficult breathing, don't take antibiotics, take care of yourself and keep body warm, good feeling and feeding and drinking, and return if you are sicker. But then the Vietnamese parents had no relationship to this hedgehog, so they wanted it to look like this, with a Vietnamese doctor and a Vietnamese child. And with this, I want to say that it's very important when you do programs or implementation project or whatever, that you look at the context and you consult with the people concerned for the intervention. Because behavior change is something individual. Of course, you can influence the individual behavior by regulations or by laws, but you can't change really the behavior of someone else. That has to come from internally. But if you want to reach a national change, it all depends on these individuals. And individuals can be at different stages of change. There is something called stages of change model. So if you are not aware of the need for change, that is that you are in the pre-contemplation mode, then why should you change? You need to realize that there is a need for change. You need to prepare for this change. You need to take action. You need to maintain this and establish a new behavior. In this case, for example, washing of hands or prescribing antibiotics in the proper way. But then it's very easy also to relapse into the previous behavior. We have been working with this model in one medical college or some hospitals in Madhya Pradesh, and we published about this stepwise approach towards the introduction of an alcohol-based hand rub and the implementation of the frontline ownership, because it's important that the people that really should change their behavior also feel the ownership of this new behavior. Then if we come back to the global action plan, you remember all these different aspects of the global action plan. It was looked at how far the implementation had come of the national action plans. This is from 2018-19. And then you can see the green colors here, green countries, they have an action plan. And the darker green, they also have funding for implementation. So as you can see, many countries, they have action plan, including India. They have also some implementation. And as I said, in India, also many states have now started developing the action plans. Then my last slide, yes, here it comes, shows the doctoral thesis where I have been supervising PhD students. And many of them are from India here, and they have data from India. This is one from Ujjain here, for example, also from Ujjain, from Odisha, from Maharashtra, and Tamil Nadu, Kerala. And they have been looking at various aspects of antibiotic use, antibiotic resistance, infection prevention and control, and the situation in the environment. So my final say here is that it's important to work together in this very difficult situation with the increasing resistance, so that the public become aware, consumer organizations, everyone should be aware of this. Healthcare providers, of course, students, policymakers, and researchers have to contribute in many different ways. So thank you very much. Sorry for the presentation mode, but I hope you could still follow the presentation. And the presentation is available with the organizers if you want to see something in detail. So many thanks.
Thank you so much, ma'am, for your presentation. I would like to ask from the participants who have joined online or offline, if they have any questions, then they can raise their hand and we can take the questions. Meanwhile, I would request Dr. Amrita to share any comments if you have.
Thank you, Professor Cecilia, for that presentation. And it's actually a very persisting topic on which you have presented, that is the overuse or misuse of antibiotics, how it could be a threat to the public, and globally it is a serious concern. And as you said, it's very important that the inputs and the collaboration and the cooperation of everybody is required to address this issue. Is there any questions from the audience? If not, I have just one question to ask to you. That is, how to deal with this issue, particularly with immunocompromised patients, and that also in a developing country. I mean, yeah, it is actually a big problem. So, from the public health point of view, I am asking you this question.
Yes. Thank you very much, Amrita. That is, of course, a very important question and comment. And I think one very important thing that everyone can do, I know it is very difficult in, especially in many low and middle income settings, but that is to try to prevent infections by by hand hygiene, for example. I know the lack of water and all that, it's a very complicated thing sometimes. I mentioned one hospital here where they had not used alcohol-based hand rub, but then together in a project, we started producing the alcohol-based hand rub for that, for those hospitals, using the WHO formula that is available. And now there is a high demand for this alcohol-based hand rub, which has a much lower price, of course, than the commercial version. So, I mean, this is something that can be done in healthcare, and I know that many healthcare settings in India work with this WHO formula to produce their own alcohol-based hand rub. And I mean, even outside healthcare settings, and that has been seen probably during the COVID pandemic, that alcohol-based hand rub is used in many places. So I think the best thing is if we can prevent infections, because then there is no discussion about use of antibiotics. But when there is an infection that needs to be treated, of course, then the healthcare providers that are treating that patient, they need to take the special circumstances into considerations. And it's also important to take, to do the bacterial cultures and to see the susceptibility pattern of the causing bacteria. And we have this concept, I didn't talk about that now, but antibiotic stewardship or antimicrobial stewardship, that where the aim is to use as narrow spectrum antibiotics as possible and for as short time as possible. There is a lot of discussions now about the treatment length, for example, for community pneumonia. Earlier it was much longer, now it has been reduced to 5 days, to 3 days, and I heard last week in a discussion it is now even discussed to be reduced even further, but of course we need studies to show which treatment length is possible to have.
Thanks a lot for that presentation. And I guess we are at the end of this session. So once again, thank you on behalf of the organizing committee. Thank you, ma'am.
Yeah, thank you very much for inviting me. Yeah, thank you.
Thank you so much, ma'am, for the presentation. Now I would like to invite Dr. R.K. Sinha, sir. Sir, if you can speak. So if you can please come to the stage to felicitate our chairperson. Thank you so much, sir. Thank you so much, ma'am. With this, we have reached to the end of all the technical sessions of the day, and we're just waiting for our guests to arrive, and then we can proceed with the valedictory session. I just request you all to kindly wait for a few minutes. Thank you.
With us today, the Professor Basu, who is the Director of CSIR-IMMT, the chief guest, and he has been supporting us, especially the City Cluster program called Bhubaneswar City Knowledge Innovation Cluster. I welcome you, sir, to this valedictory ceremony of the NESA annual conference. And you have been watching Professor Amal since yesterday and Mr. Sinha also, both are from the NESA and have been supporting this conference. And really thankful to you, sir, and welcome both of you to this valedictory session. And my own colleague, Prasant, who is the CEO of City Cluster. I welcome all of you to this valedictory session. It's not the end of it, just the beginning. I realized I've been searching about NESA since yesterday, what NESA has been doing, NESA has done so far. I have been told also today, now Mr. Sinha was telling about the NESA is the pioneer institutions or the organization which has been promoting environmental based research in the country. And so I learned that since yesterday, people have been embedding a lot of technology, solutions, scientific developments. So at the end, I expect these discussions should not end in terms of a paper or a, what you call, patents only. Can you build something out of it and develop a solutions which can be deployable, affordable, and can be scalable? Because I'm a man from technology towards commercialization, towards enterprise creation, and I expect at the end, once you go back, don't keep it in your laboratories or don't keep it in your, what you call in the experimental only. Take it to the field, take it to the commercial level, talk to industries, talk to the communities, talk to the policymakers. So this, I again welcome all of you. I'll not take much time because this is what the day for Professor Basu is to speak, that how the department or the CSIR-IMMT is doing a lot of pioneering work, which is now deployed, going to be deployed in many of the cases. So with this, I again, thank all of you for attending this conference, and I thank NESA for supporting this one. I thank all my colleagues who have been a part of this. Thanks to all of you. Thank you.
Thank you so much, sir, for the address. Now I would like to invite Professor Javed for the brief address.
Very good afternoon. This is a valedictory session of today's international conference, and we have chief guest Professor S. Basu, Director CSIR-Institute of Minerals and Material Technology, and other dignitaries of the dais, and all the delegates, awardees, and special invitees. First of all, I would like to extend my sincere thanks to the chief guest of today's valedictory session, Professor Basu, who spared his valuable time from his office and is passing some time with us to guide us and to see the progress of last 2 days, the business, the academic business which we have done here. That is wonderful. I am very much impressed about the outcome of this 2 days conference. So total papers, I would like to inform you, sir, that near about 70 papers have been presented in this conference. 52 oral through invited talks, and the others are oral presentation. So the breakup is like this, that 22 and 30 were presented in the oral presentation yesterday and today, total 52, and 17 papers through invited talks here in these 2 days. So this is the academic business, and this is the output for which we were waiting, and we organized and we used the infrastructure and all expenses. So only because of passing on the information and technology to our younger scientists, to our young technologists. So that is one of the benefits. And other benefit, that is exchange of views, what we have done in the last few years on this big issue, that is promoting of environmental technologies for waste management and sustainable. Sir, I would like to inform you that very good papers were presented here on minerals and materials and mines. So this is a new information for us, that here in these few states of our country, the mines work, scientific work on mines, on materials are going on here. And I will be very happy that so far the publication of the proceeding is concerned. So from NASA side, the efforts will be done. And I would like to request the honorable guest of the day, Professor Basu Saab, for taking interest in the publication of this proceeding, because that will be a good output of this conference, international conference. So this is the summary of the conference of these 2 days. And sir, we are also publishing the academic journals from the NASA. Our publications are very prominent: the International Journal on Agricultural Science, International Journal on Environmental Science, International Journal on Biological Sciences, Indian Journal of Unani Medicine, and a monthly newsletter is also there. And we cover the different aspects related with the environmental education. So these are our, aims and object of the academy. And every year we organize the annual function, and very hope in next year, 2022, we will announce very shortly the venue of the annual conference, and the date and everything will be communicated to the delegates through website of the NASA Academy. So in the last, I would like to thank the organizers of this conference, the organizing committee, and the founder of this institution, who was very keen and who permitted us to organize this program here with zeal and zest. So all faculties, involvement of all faculties members in this conference is highly appreciated at my level. So with these words, I again extend my warm welcome to the chief guest and other dignitaries and all the awardees of yesterday and today. We will give awards by the hands of the chief guest. Thank you very much, sir.
Thank you so much, sir, for this address. Now, next I would like to call Dr. R.K. Sinha, sir, to address the gathering. Thank you.
Again, namaskara. I try to speak little bit of Odia, but today I have a duty to perform. It is customary that for the record, we should announce all the names of awardees who have been selected out of hundreds of applications. Just tell you the brief background. We have first screening at the administrative level. Then we have an internal committee of experts who scan and go through all the applications minutely. And then we have a committee of experts, eminent scientists and professors from outside NASA. They are not even members of NASA. So these are 3 layers of screening, and I'm very happy to announce that the successful applicants who have been awarded, the highest award is for fellowship. And here are the names. Please hold your applause for the end, because it's a long list, and then we can applaud all of them collectively, except for probably Professor Mrityunjay. This first name is Professor Shakil Ahmed Khan, Dr. Sandeep Kumar Bera, Professor Raghuvendra Singh, Dr. Veeraswamy Sejan, Dr. Artabandhu Sahu, Dr. Ramchandra Guru Prasad, Dr. Prakash M. Halamai, Dr. Kuladeep Jana, Dr. Sanjay Singh Rathore, Professor Tarun Kumar Thakur, Mr. Sitendu Mandal, Dr. Murugan C, Professor K. Pandian, Dr. Konda Srinivas Reddy, Dr. Mrityunjay Suar. I think we can applaud him. Congratulations, Dr. Suar. Dr. Kali Sanjay, Dr. Vinay Kumar Sharma, Dr. Ali Anwar, Dr. Mahadev Swami, Dr. T. Satyanarayana Reddy, Dr. Rajesh Arora, Dr. Gajanan Triambak, Professor Galla Rajitha, Professor Narsi Ram Bishnoi, Dr. Jitendra Kumar Sundare, Dr. C. Kanan, Dr. K.T. Chandrasekhara. The next is the eminent scientist of the year 2021, Dr. Pramod Kumar, Dr. Vakar Ehsan, Dr. T.S. Harsha, Dr. Sundar Gopal Sridhar, Dr. Chandrasekhara YP, Dr. Nagaraj Basave Gowda, Dr. Sachin Suresh Sarushe, Dr. Suraj Kumar Tripathi, is he here in the hall? Dr. Prakash Gudappa Patil, Dr. Sanjeev Kumar Das, Dr. Smita Shukla, Dr. Angasuman Chanda, Dr. Pradeep Kumar, Dr. Naveen Kumar Dhal, Dr. Josna Penchala Neni, Dr. Suhail Parvez, Dr. Rajni Nagula, forgive if any wrong pronunciation, because India has a diverse place, different languages, different surnames. Dr. Shambhu Lingappa BE, Dr. Shirekar Pant, Dr. Lakhwat Ram Singh, Dr. Wahid Khawar Balwan, Dr. Suhaib A. Band, Dr. S. Milatano Rabu, Dr. L.M. Suresh. The next category is Scientist of the Year 2021, Dr. Syed Zahir Hassan, Dr. Giri Babu Nelli, Dr. Ram Krishna Rao Muthaila, and we have Environmentalist of the Year 2021, Dr. Hemraj Shippa, Dr. Parvez Ahmed Rather, Dr. Sankha Chakravarti, Dr. Sanak Ray, Dr. Shivanandaji Hani Chanal, Dr. Rosalind Das, Dr. Sanat Kumar Dvedi, Dr. R. Jayashri, Dr. Sanyasi Naidu Dadi, Dr. Pawan Kumar. Next is Green Technology Innovative Award 2021, Dr. Guru Prasad Mopala, Dr. Ufana Riaz. Then we have exclusive award for women, Women Excellence Award 2021, Professor Upasna Bora Sinha, Dr. Amrita Mishra, Dr. Amrita Mishra is here. Let's applaud her, of course. Those who are here, please, you can give a shout. Dr. Sumayan Parveen, Dr. Kavita Tyagi, Professor Rachna Singh. I can see Professor Rachna Singh also, yes. NESA Distinguished Award 2021, Dr. Ennamuri Muralinath, Dr. Sudipta Kumar Ghurai, Dr. Ram Raju Nagarjuna Kumar, Dr. Sarita Marela, Dr. Syed Shahib Hassan. And here comes the most promising award, the Young Scientist of the Year 2021. We have so much confidence and faith on you, young scientists. Starting with Dr. Mayuri Chabu Kadhara, Dr. Faisal Rashid, Dr. Mumtaz Ahmed Numani, Dr. Sarvesh Kumar, Dr. Nisha Sharma, Dr. Manoj Kumar, Dr. Priya Padurang Durao, Dr. Pirzada Yasir Yusuf, Dr. Lakharam, Dr. P. Rupa Saujanya, Dr. G. Senthil Kumar, Mr. Rahul Ratnakar Mahamuni, Dr. Pathor Rajendra Shashank, Dr. P. Thimme Gowda, Dr. Mahendra Kumar M, Dr. Niranjana M, Dr. Chetan Chauhan, Dr. Santosh Shah Chobe, Dr. Abhijit Devnath, Dr. Amit Kumar, Dr. Kiran B. Gaikwad, Dr. Dilip G. R, Dr. Lata M, Dr. Asha Sahu, Dr. Tulsi Naik KS, Dr. Muhammad Reshma Anjum, Dr. Pooja Kaushik, Dr. Timanna HN, Dr. Neha Sami. And we also have a Junior Scientist Award for even the youngest. Dr. Mahesh Gajnaru Basappa, Mr. Afaq Ahmad Dar, Mr. Shadab Ali, Dr. V. Niruvana. Dr. Shadab Ali is here? Okay, congratulations. Dr. V. Niruvana, Dr. Agniva Mandal, Mr. Ananyo Jyoti Mishra. Who is Jyoti Mishra? Okay, good. Mrs. Vinutha R. Bhatta, Mrs. Yarama Reddy Rupa, Mr. Niklesh Jordar, Miss Vishnu Priya Divedi, Miss Neha Naz, I think she is here. No? Neha Sami, okay. Dr. Rajanand Hiramat, Dr. Santosh Bhukal, Mr. Nihal Gujre, Miss Nidhi Sharma, Miss Sonali Satapathy, Dr. Sudarshan P, Miss Meenu Rani. So let's give them a collective round of applause for all the winners and future winners. Congratulations, all the winners. God bless you.
Thank you so much, sir. Now I'd like to invite our chief guest, Professor Basu, Director CSIR-Institute. Just to brief about Dr. Basu, he has done his PhD and MS in Chemical Engineering from Indian Institute of Science, Bangalore. Prior to taking over as a director of CSIR-IMMT, he was a professor and head of Chemical Engineering Department at IIT Delhi. He has a vast work experience on development of energy materials and its application to energy conversion and storage devices, example as a fuel cells and supercapacitor with more than 200 publications. He is a fellow of National Academy of Science of India, Indian National Academy of Engineering, Royal Society of America, Inc. With this, I take this pleasure to invite you, sir, on this.
Good afternoon to all of you, respected Professor Javed Ahmed, Professor Mrityunjay, Dr. R.K. Sinha, and all the dignitaries, Dr. Singh, and all the dignitaries of the dais, and the delegates, and the participants and students, those who are online, listening to us, the valedictory session of WMSD 2021, which is organized by BCKIC and NESA, and then IMMT also is partner here with KIIT and CIPET. So I'm very happy that this has come to an end, and it's a happy ending for all of us, that this is a very important event. The one side, you talk about the sustainability. The other side, of course, is the waste management. They go side by side, and specialized, especially the civilization that we have about close to 5,000 years old, and it's a huge population in India, requires such intervention with such a huge population. If you have to have growth, GDP growth at 10% or more, or if you elevate the people from a below poverty line to above poverty line, you require really huge growth and huge use of material, minerals, all sorts of materials and minerals that you require for general use. It could be day-to-day use, it could be health, it could be transportation, it could be your clothing, it could be building houses, it could be food, anything you talk, agricultural waste. So if you really have a equality amongst us in India and throughout the world as well, all continent together, whether it's sub-Saharan Africa or it's Asia or Europe or Siberia or North and South America, Australia, New Zealand, and everything North, even North Pole and South Pole, everywhere, whoever is living in this earth, if you have equal life for everyone, then you require huge materials to be developed, to be used, and to be recycled. That is what all about the waste management. And then only it is possible that you have a sustainable living. I mean, if you don't recycle, then how long you're going to use the minerals from the earth crust, how long you're going to emit emission will be there because of your use of if it's a natural gas or petroleum or it's a mineral coal, how long this will continue. It is not possible. So you have to recycle. You have to recycle the solid waste, you have to recycle the effluent, the liquid wastes after doing purification, and you have to also recycle your air, because you cannot emit CO2 or greenhouse gases on, and that will be not a sustainable living. So I was trying to concentrate on the area that we work on, mostly in minerals and materials sector, that the institute I come from. And in this sector, I'm from Orissa, and Orissa generates huge amount of wastes. So the number, if you hear that if we generate a 1 million ton, generally production in a year is about 111 million tons of steel, and you almost equal amount of gang or waste material, if not more, little more than that, we generate waste. That means it could be form of fines, slimes, or all kind of gang material, slag, sludge that we generate. So our annual production is 111 million tons of steel, and we would like to go to about 300 million tons of steel by another 10 years time. And that would mean optimum production, which will give you bridges, roads, buildings, whatever, metro railway, wherever you require steel. And as I was talking about the equality in living, you require those things. You have to provide the houses, hospitals, schools, and colleges and universities. So you require such amount of steel. So then you also generating an equal amount, if not more, amount of waste. And that waste you just cannot dump. You have to use it. These wastes also contain a lot of valuable material, also contain iron and other valuable material. Similarly, we generate maybe about 4 million tons of aluminum. We are one of the highest aluminum producer of the world, highest in Asia, and we have huge bauxite deposits in Orissa. And if we generate about 4.5 million tons of aluminum, you generate about even 5.5 or 6 million tons of red mud. Or we generate also along the red mud, we also generate other material with that is the aluminum dross. Aluminum dross, of course, is very small amount. Let's say about 0.12 million tons of aluminum dross, but we generate about more amount, about 5.56 million tons of red mud. And this is again containing titanium, containing iron, containing alumina, and the rare earth. And so there's a lot of scope to extract more and more, and then not leave behind this garbage or waste material in the plant or anywhere else, and where there will be leaching, and then there will be, of course, the unwanted material will go to the streams, which happens in chromite overburden in Sukinda every day, because there's a big chromite mine here in Orissa. This is about the mineral aspects and what we can do. And then I was talking about that, are you going to mine more and more? No. So there's a concept called urban mining. So your steel, your copper, zinc, your manganese, aluminum, all required to be recycled. So used steel, which we are doing it, the secondary steel sector, they does that, the scraps, then they make rebars and you use for house building and all. But you require more. Regular aluminum, steel, tin, copper, all zinc, everything need to be recycled. So we call it urban mining. And not only that, even if you go to the sector of, let's say, e-mobility, huge requirement of rare earth, huge requirement of lithium-ion battery and lithium-ion or lithium oxide or lithium carbonate, huge requirement of cobalt, manganese is required. And if the e-mobility really have to take forward, that means if you require to have, let's say today, it is about, I think about 20 gigawatt hour of lithium-ion battery is there in India, which is used mostly for storing energy in the renewable sector, and of course in the sectors of mobility less, but it is coming up, and then all these electronic devices. So which is, I said, about 20 gigawatt hour. And shortly, if e-mobility takes shape, that means if e-mobility happens for every common person, then this, which is 20 gigawatt hour of battery, will shoot up to about 500,000 million gigawatt hours of battery to be in another 10 years time. Then you generate a lot of waste, not only from your e-mobility, from your mobile phone, from your laptop, and many devices all require energy, and lithium-ion battery is one of the way of getting that storing of energy and the releasing of energy. Charging, discharging is possible. So you have this lithium to be recycled, you require manganese to be recycled, you require cobalt to be recycled, iron to be recycled in iron phosphide cathode material in battery, and so on and so forth. So I just moved away from minerals, a material sector, to lithium-ion battery, which is a under material sector, but then huge requirement of lithium-ion and cobalt and manganese that I talked about need to be recycled. Now, what about the e-mobility, the motor? The electric motor consists of magnets, and these magnets are made of rare earth, samarium cobalt, or neodymium iron boron. And so you require huge amount of neodymium, huge amount of samarium. So where they will all come from? There are rare earth. You just keep rare earth, of course, namesake, you understand that what is the meaning of rare earth. So it's not available. Even that wherever available, it's in small quantity, ppm level. From there you have to go to the percentage, and then you have to actually make those magnets. But then recycling of electric vehicle is important. That means you have millions of electric vehicles on the road. After five years or 10 years, they will lose their lifespan, and then the electric motors, which is having those magnets, need to be recycled, in the sense that samarium cobalt need to be again, or NdFeB magnet, neodymium need to be re-extracted from the used or spent magnets, which is not of any use. You cannot magnetize it anymore. And then you have to make again NdFeB magnet or neodymium iron boron magnet or samarium cobalt magnet, which are used in electric motors, in e-mobility, and many other places. Any normal today, in the normal car, all the actuators are based on magnets, and these magnets are all having samarium cobalt or NdFeB. And so you need recycling of them. So where the role of urban mining comes into force, and recycling and reuse is the mantra, and reduction. So 3R we talked about: recycle, reuse, and reduce. This 3R is important, and they're all connected to your solid waste management, or if I remove the solid waste, I mean, it's just waste management and sustainable living, which is what is today's 2 days of conference all about. That if I do not recycle, reuse, and reduce, then I really cannot connect the waste management to the sustainable living. That is what is important, and for India is such important, which is having such big population, to cater with all the standard of livings. Then you have to have such kind of avenue, otherwise it is not possible. Even the countries like China also required a similar thing, and even Europe have understood, because they are equally densely populated as India. The square areas or square miles of the area is very small in Europe, but hugely packed country, the whole of Europe. And they have understood that sustainable living is very important, and only by recycling it is possible. So if you go to any European countries, it is it is in their mind and body that they collect all the material and try to recycle. As it is, whatever can be recycled, processed and then recycled, or re-extracted and recycled, which is already there in 20 years, not today, for last 20 years in Europe. Equally important is US or North America and South America, especially Canada and United States also have started doing it for last 20 years, because they also would understand that that's a huge country. They have huge resources, both Canada and US. But having said that, their population is low, less densely populated than Europe. But they also understood that one day this will hurt them. And they also have gone to recycling of whatever is possible. Although they waste a lot, but India cannot afford. Being a poor country, this is the mantra, this is how you need to move forward. And I really thank organizer to take such an important issue and organizing in the COVID time, organizing such a beautiful conference with the right mindset and title, and NESA to come forward, KIIT to come forward, and our Bhubaneswar cluster to come forward with IMMT. Of course, the knowledge partner like IMMT and CIPET and KIIT and others. I'm very happy, and I'm sure in future we will have more and more such conferences where we can have in full physical mode, and we need not be in a hybrid mode that today there's 2 days of conference being organized on 12th and 13th of December. And I wish great success, and I'm happy that they have encouraged so many people to give the award. Of course, there are 2 different years being mentioned, but I think award, of course, is given to chosen ones who have done exemplary work, a work that is worth mentioning and awarding, but also giving many awards to, in such kind of area where you create a kind of encouragement, kind of awareness among all the participants, those who are simply participating as a delegates. I mean, that in future, it will surely help us. The small thing gets added up. And I hope that in coming years, this WMSD-2022 or 23 will be much more successful, much more wider participation. And in practice, you do that. I mean, one thing is important for us in India is to practice. What you say, what you preach, whether you do it, whether you are ready to, all of you go back home today, you generate waste. Do you segregate your waste? Do you have a wet waste separately done, a dry waste separately done? Do you keep mercury away from the normal waste? Do you keep your battery, which has some poisonous material, away from the normal wet waste and the dry waste? Do you keep the plastic separately or not? I know we learn all these things in school, and I've seen in practical sense that when kids go out after class 10 or 12 in the college, then they see that many of them not obeying it. And I have learned in the school, and I've seen my sons looking for a garbage bin to put his plastic bags, but he doesn't find it. And then he says, Papa, I was looking for it, but I'm not able to find any garbage bin to put my plastic. So I was carrying at my pocket. Even I do carry in my pocket if I cannot find place to put my my waste material. This is very common, but slowly, I think all of you are more educated. We have a mass of people whom we are not able to send to the school. We have a mass of people who are not being educated enough to tell the importance of segregation of waste and putting the waste in a designated area. We are not able to. I don't blame them, because they are not being told. They are not being given school education. That's a irony. That's a true fact. And I know the KIIT is doing extremely good work in this area, and we have the responsibility. At least those who are educated, those who got a proper education, you see, you force yourself and force the other person next to you sitting, put the garbage in a proper place. And in the normal Indian home, everybody feels I keep my home clean means I am very okay. And I dump everything on from my balcony or from my room downstairs is very okay. And my room is clean. I don't care about what is lying on the street or what is lying on the footpath or the road. We have that tendency. Please remove that from your mind. And please, even you have to walk 10 steps, 100 steps, 500 steps to put your garbage in a garbage bin, do that. That is the practice you need to do. And many of us, we don't do that. And that is how, even if my telling it will not make any sense unless I practice and you practice and tell others to practice it. And it is also connected to waste management. It is also connected to the sustainable living. If I do not get my garbage in a segregated form, I cannot take my biomass or bio waste to generate energy, because plastics will be coming there and it will incinerate it, or maybe my process is through a biochemical route where the plastics will not get into, will clog it and will not get disposed of. So there are many technical issues where we require segregation of garbage and work on it. And I'm sure if I have told you, I told you the truth and you know it very well. And if I am able to at least sensitize you towards this, I've done my part being in this conference towards the end of this valedictory function. Thank you very much for giving me time, and I wish you best luck.
Thank you so much, sir, for this insight. Moving ahead, now, as sir has also already mentioned us about the winners of respective genres, so I would take this to invite all the physically present awardees who are there here. So we'll just call out the names and we request you to come to the dais, and I request Basu sir to kindly felicitate them with their awards. First, we will move with the NASA Scientist of the Year. I would like to call Dr. Syed Zahir Hussain. Request you to kindly give him a big round of applause. Dr. Syed Zahir Hussain, as a scientist, Chief Petroleum Research Wing, Gujarat Energy Research and Management Institute, recent Gandhinagar, Gujarat. Thank you so much, sir. Moving on to the next, we are going ahead with the NASA Environmentalist of the Year 2021. And I would like to call Dr. Rosalind Das, Associate Professor, FM University, Dr. Sanat Kumar Dwivedi, Assistant Professor, College of Agriculture, OUAT, and Dr. Shankar Chakraborty, Assistant Professor, Department of Biotechnology, KIIT. Kindly give them a big round of applause, everyone. Thank you. Next, I will call Dr. Sanat Kumar Dwivedi to the stage. Next, I would like to call Dr. Shankar Chakrabarti to the stage. They would. Moving ahead with the next award, we are going ahead with the Women Excellence Award 2021. And I would like to call Professor Rachna Singh, Department of Biotechnology, University, and Dr. Amrita Mishra, Assistant Professor, Department of Molecular Biology, KIIT. Moving next to the special category, this NASA Distinguished Award. I would like to call Dr. Sarita Marella, Associate Professor, Nanotechnology Laboratory from Tirupati. Moving ahead with the NASA Young Scientist of the Year 2021, I would like to call Dr. Manoj Kumar, the Department of Environment and Sustainable Development, Central University, Gujarat. Next, I would like to call Dr. G. Senthil Kumar, Associate Professor, Department of Rice, Tamil Nadu University, Coimbatore. Okay, I think he is not there here. So moving on with the next, I would like to call Dr. Amit Kumar, Postdoctoral Fellowship, Department of Geology, BHU, Uttar Pradesh. Next, I would like to call Ms. Neha Sami, PhD pursuing Department of Biosciences, Jamia Millia Islamia, New Delhi. Moving ahead with the next category, NASA Junior Scientist of the Year Award 2021. I would like to call first Mr. Shadab Ali, Lecturer, Department of Botany. Next, I would like to call Mr. Ananya Jyoti Mishra, Senior Research Fellow, Department of Bioprocess Engineering Lab, KIIT. Next, I would like to call Ms. Vishnu Priya Dwivedi, PhD Scholar, Department of Computer Sciences, Silicon Institute of Technology, Bhubaneswar. And at last, I would like to call Ms. Sonali Satpathy, PhD Scholar, Department of Botany at Utkal University. Do we have? Okay. I would like to call all the awardees to the stage for a group photograph. Congratulations to all the awardees once again. So now we are left with the winner announcement of the poster presentation that happened simultaneously parallel to this session. So I'll start with the third position. Congratulations, Neelam Bhagel and SK Kabi for the third prize in the oral presentation. The second prize of the oral presentation goes to Mr. Arpan Ghosh, KIIT, School of Biotechnology. And the first prize goes to Kavya Bisaria, Department of Biotechnology, Amity University, Noida. We are unaware if they are present here online. Yeah. Okay. Congratulations, Kavya. Mr. Arpan, are you there here? Thank you so much, sir. At last, sir, I would like to call Mutinder sir to felicitate the organizers of this event. I would like to call Dr. Prashant sir for the felicitation. Sir, please. Felicitation of the organizers. So just a small thing, we just want to felicitate the organizers of this event too, without whom this event would not have been possible. So okay. Thank you, Dr. Prashant Singh, Dr. Shishendu Banerjee, Dr. Shankar Chakraborty, Dr. Sudhir Jha, Kalyani, and Mr. Saikat Gupta. Thank you so much. Now I would like to call Prashant sir for vote of thanks.
Thank you, Aryan. A very warm good afternoon to the dignitaries on the dais, dignitaries of the dais, online participants, all the awardees of NISA 2020-21. It has been great pleasure to host all of you, some of you in the campus of KIIT, as well as some of to you over online. The participants were very enthusiastic, and I'm thankful to all the participants, including speaker, delegates, industry people, students, for coming to the Bhubaneswar, and many of them joining online. We have been fortunate to have some of the eminent persons from academia and industry working on the environmental sustainability, and I'm sure that the learning of the conference are going to go in a long way in the sustainability of our culture, our environment, our growth. I feel honored and privileged to get the opportunity to propose this vote of thanks during the valedictory session. On the behalf of organizing committee, I express my gratitude to our honorable chief guest, Professor Sudhasatwa Basuji, Director CSIR-IMMT, and touching the important topic of reuse, recycle, as well as re-extract. So those wisdoms are going to be used by many of the people. I hope it is going to be followed. I'm thankful to Professor Javed Ahmed, President NESA, for sharing the vision of the Academy and detailed introduction of the International Conference on the WMSD-2021. I'm also thankful to R.K. Sinhaji, Executive Secretary NESA, for his constant encouragements. We have deep sense of appreciation for NESA for conducting this year international conference in Bhubaneswar, and we look forward to further collaboration in future. I sincerely thank organizing partners from the city, KIIT, CSIR-IMMT, CIPET, and Environment and Social Development Association New Delhi for seamlessly connecting for the conference, as well as organizing the pre-conference workshops. One was organized at CSIR-IMMT, Dr. M.G. Sujana, she could not come. Thank you, ma'am. Also, the second one was organized as CIPET on the biopolymer by Dr. Smita Mohanty. Thank you, ma'am, for your all the efforts for organizing these workshops. I'm very much thankful to the sponsors of the conference, Saitua and Ipendo. Without their generous financial support, it would not have been possible to arrange all the logistics in time. I must mention my deep sense of appreciation for Professor Bhubaneswar, Director General R&D KIIT and Chairman BCKIC. It had been not possible to organize this conference without your constant support, and I cannot name the number of efforts done by you. Yes. For the conference conveners, Dr. Kali Sanjay from CSIR-IMMT, Dr. Smita Mohanty from CIPET, and Dr. Suraj Tripathi from KIIT. Thank you very much for being the convener and organizing, helping us every time whenever the need arises. I thank Dr. Srinivas Patnaik, Dean, Kalinga School of Biotechnology, for all the support and strength extended towards the conference. I also thank the faculty members of the KSBT for all their contribution, and thank the KIIT administration for providing us with the possible logistic support towards organizing this event. Special mention to all the members of the organizing committee, and some of them really worked extensively. I must mention the support of the team members, Arpan, Riya, Nitika, Meera, Ananyo, Pranjal, Swati, Dhruti, Sai, and Vedanta. Vandana. Extended contribution from Paulji, Parveji, and Himanshu, and entire auditorium team for making the event, yes, successful. I sincerely congratulate all the NESA awardees and all the NESA members who are joining online, live members. Thank you very much for being online, and hope to see you next year as well. Once again, I thank you once again for being in the conference. Thank you very much. So tea is at the backside, high tea. Please join us for the tea. Thank you. Thank you very much. You have been wonderful participants. Thank you.
Yeah.
Congratulations to Mr. Arpan Ghosh for getting a second prize in the oral presentation of